A photograph shows about 20 colorful hot air balloons at varying stages of inflation. Some are deflated, while others are inflated. 3 of the balloons are off the ground and are visible against a bright blue sky. Figure 9. 1. The hot air inside these balloons is less dense than the surrounding cool air. This results in a buoyant force that causes the balloons to rise when their guy lines are untied. Credit: Modification of work by Anthony Quintano. Chapter outline 9.1 Gas pressure 9. 2. Relating pressure, volume, amount, and temperature. The ideal gas law 9. 3. Stoichiometry of gaseous substances, mixtures, and reactions 9. 4. A fusion and diffusion of gases 9. 5. The kinetic molecular theory 9. 6. Non-ideal gas behavior. We are surrounded by an ocean of gas, the atmosphere, and many of the properties of gases are familiar to us from our daily activities. Heated gases expand, which can make a hot air balloon rise, figure 9.1, or cause a blowout in a bicycle tire left in the sun on a hot day. Gases have played an important part in the development of chemistry. In the 17th and 18th centuries, many scientists investigated gas behavior, providing the first mathematical descriptions of the behavior of matter. In this chapter, we will examine the relationships between gas temperature, pressure, amount, and volume. We will study a simple theoretical model and use it to analyze the experimental behavior of gases. The results of these analyses will show us the limitations of the theory and how to improve on it. Learning objectives: by the end of this section, you will be able to define the property of pressure, define and convert among the units of pressure measurements, describe the operation of common tools for measuring gas pressure, calculate pressure from manometer data. The Earth's atmosphere exerts a pressure, as does any other gas. Although we do not normally notice atmospheric pressure, we are sensitive to pressure changes. For example, when your ears pop during takeoff and landing while flying, or when you dive underwater. Gas pressure is caused by the force exerted by gas molecules colliding with the surfaces of objects. Figure 9.2. Although the force of each collision is very small, any surface of appreciable area experiences a large number of collisions in a short time, which can result in a high pressure. In fact, normal air pressure is strong enough to crush a metal container when not balanced by equal pressure from inside the container. The left side of this figure includes a graphic of the Earth with an inverted rectangular prism extending from a point on it. Near the top of the image, the label square-inch column of air molecules is connected to the prism with a line segment. This label is also connected with a line segment to a downward pointing arrow at the right side of the figure. Beneath the arrow is a red circle labeled atmospheric pressure. A narrow rectangle with a dashed line border extends from the bottom of the arrow vertically through the circle. Directly beneath this rectangle at the lower edge of the circle is a hand with a thumb appearing to be resting on a tabletop. The thumb is connected with a line segment to the label, 14.7 pounds of pressure on 1 square inch. The red circle is sitting on top of the thumb. Figure 9. 2. The atmosphere above us exerts a large pressure on objects at the surface of the Earth, roughly equal to the weight of a bowling ball pressing on an area the size of a human thumbnail. Link to learning a dramatic illustration of atmospheric pressure is provided in this brief video, which shows a railway tanker car imploding when its internal pressure is decreased. A smaller scale demonstration of this phenomenon is briefly explained. Atmospheric pressure is caused by the weight of the column of air molecules in the atmosphere above an object, such as the tanker car. At sea level, this pressure is roughly the same as that exerted by a full-grown African elephant standing on a doormat, or a typical bowling ball resting on your thumbnail. These may seem like huge amounts, and they are, but life on Earth has evolved under such atmospheric pressure. If you actually perch a bowling ball on your thumbnail, the pressure experienced is twice the usual pressure, and the sensation is unpleasant. In general, pressure is defined as the force exerted on a given area. Letter 1D443 equals letter 1D439 letter 1D434. Note that pressure is directly proportional to force and inversely proportional to area. Thus, pressure can be increased either by increasing the amount of force or by decreasing the area over which it is applied. Pressure can be decreased by decreasing the force or increasing the area. Let's apply this concept to determine which exerts a greater pressure in Figure 9.3, the elephant or the figure skater. A large African elephant can weigh 7 tons, supported on 4 feet, each with a diameter of about 1.5 ft, footprint area of 250 and 2. So the pressure exerted by each foot is about 14 lb/2. Pressure per elephant foot equals 14,000 lb times 1 elephant 4 feet times 1 foot 250 and 2 equals 14 lb/2. The figure skater weighs about 120 pounds, supported on 2 skate blades, each with an area of about 2 in 2, so the pressure exerted by each blade is about 30 lb/2. Pressure per skate blade equals 120 lb skater times 1 skater 2 blades times 1 blade 2 and 2 equals 30 lb/2 even though the elephant is more than 100 times heavier than the skater. It exerts less than 1/2 of the pressure. On the other hand, if the skater removes their skates and stands with bare feet or regular footwear on the ice, the larger area over which their weight is applied greatly reduces the pressure exerted. Pressure per human foot equals 120 lb skater times 1 skater 2 feet times 1 foot 30 in 2 equals 2 lb/2. This figure includes 2 photographs. Figure A is a photo of a large gray elephant on grassy, beige terrain. Figure B is a photo of a figure skater with her right skate on the ice, upper torso lowered, arms extended upward behind her chest, and left leg extended upward behind her. Figure 9.3. Although A, an elephant's weight is large, creating a very large force on the ground, B, the figure skater exerts a much higher pressure on the ice due to the small surface area of the skates. Credit A. Modification of work by Guido de Raz. Credit B. Modification of work by Ryusuk Yagi. The SI unit of pressure is the Pascal Pa, with 1 Pa equals 1 nm2, where N is the Newton, a unit of force defined as 1 kg/ms2. 1 Pascal is a small pressure. In many cases, it is more convenient to use units of kilopascal. 1 kPa equals 1,000 Pa, or bar, 1 bar equals 100,000 Pa. In the United States, pressure is often measured in pounds of force on an area of 1 square inch, pounds per square inch psi, for example, in car tires. Pressure can also be measured using the unit atmosphere, ATM, which originally represented the average sea level air pressure at the approximate latitude of Paris, 45 degrees. Table 9.1 provides some information on these and a few other common units for pressure measurements, pressure units unit name and abbreviation definition, or relation to other unit Pascal Pa. 1 Pa equals 1 nm2 recommended IUPAC unit kilopascal, kPa. 1 kPa equals 1,000 Pa pounds per square inch. Psi, air pressure at sea level is 7 psi atmosphere, ATM. 1 ATM equals 101,325 Pa equals 760 torr air pressure at sea level is tilde 1 ATM bar, or B. 1 bar equals 100,000 Pa exactly, commonly used in meteorology millibar, mbar, or MB, 1,000 mbar equals 1 bar inches of mercury, in. Hg, 1 in. Hg equals 3386 Pa used by aviation industry. Also some weather reports torr 1 torr equals 1,760 ATM, named after Evangelista Torricelli, inventor of the barometer millimeters of mercury. Hg. 1 Hg tilde 1 torr. Table 9. 1 Example 9. 1 Conversion of pressure units. The United States National Weather Service reports pressure in both inches of Hg and millibars. Convert a pressure of 29.2 in Hg into A torr B ATM C kPa D mbar solution. This is a unit conversion problem. The relationships between the various pressure units are given in Table 9.1a, 29. 2 in Hg times 25. 4 mm1 in times 1 torr 1 Hg equals 742 torr, B. 742 torr times 1 ATM 760 torr equals 0. 976 ATM, C. 742 torr times 101. 325 kPa 760 torr equals 98. 9 kPa, D. 98. 9 kPa times 1,000 Pa 1 kPa times 1 bar 100 000 Pa times 1000 mbar. 1 bar equals 989 mbar. Check, you're learning a typical barometric pressure in Kansas City is 740 torr. What is this pressure in atmospheres, in millimeters of mercury, in kilopascals, and in bar? Answer: 974 atm, 740 mhg, 987 kPa. 987 bar. We can measure atmospheric pressure, the force exerted by the atmosphere on the Earth's surface, with a barometer, figure 9.4. A barometer is a glass tube that is closed at one end, filled with a non-volatile liquid such as mercury, and then inverted and immersed in a container of that liquid. The atmosphere exerts pressure on the liquid outside the tube, the column of liquid exerts pressure inside the tube, and the pressure at the liquid surface is the same inside and outside the tube. The height of the liquid in the tube is therefore proportional to the pressure exerted by the atmosphere. This figure shows two barometers. The barometer to the left contains a shallow reservoir or open container of mercury. A narrow tube extends upward from the reservoir above the reservoir. This tube is sealed at the top. To the right, a second similar setup is shown with a reservoir filled with water. Line segments connect the label vacuum to the tops of the two narrow tubes. The tube on the left shows the mercury in the reservoir extending in a column upward in the narrow tube. Similarly, the tube on the right shows the water in the reservoir, extending upward into the related narrow tube. Double-headed arrows extend from the surface of each liquid in the reservoir to the top of the liquid in each tube. A narrow column or bar extends from the surface of the reservoir to the same height. This bar is labeled atmospheric pressure. The level of the water in its tube is significantly higher than the level of mercury in its tube. Figure 9.4 in a barometer, the height h of the column of liquid is used as a measurement of the air pressure. Using very dense liquid mercury, left, permits the construction of reasonably sized barometers, whereas using water, right, would require a barometer more than 30 feet tall. If the liquid is water, normal atmospheric pressure will support a column of water over 10 meters high, which is rather inconvenient for making and reading a barometer. Because mercury, Hg, is about 13.6 times denser than water, a mercury barometer only needs to be 113.6 as tall as a water barometer, a more suitable size. Standard atmospheric pressure of 1 atm at sea level, 101,325 Pa, corresponds to a column of mercury that is about 760.29.92 in. High. The torr was originally intended to be a unit equal to 1 millimeter of mercury, but it no longer corresponds exactly. The pressure exerted by a fluid due to gravity is known as hydrostatic pressure, P. Letter 1D45D equals letter 210 letter 1D70 C letter 1D454, where h is the height of the fluid, rho, lowercase Greek letter rho, is the density of the fluid, and g is acceleration due to gravity. Example 9. 2. Calculation of barometric pressure. Show the calculations supporting the claim that atmospheric pressure near sea level corresponds to the pressure exerted by a column of mercury that is about 760 high. The density of mercury equals 13.6 g/cm3. Solution: the hydrostatic pressure is given by P equals h rho, with h equals 760, rho equals 13.6 g/cm3, and g equals 9.81 ms2. Plugging these values into the equation and doing the necessary unit conversions will give us the value we seek. Note: we are expecting to find a pressure of 101, 325 Pa. 101, 325 letter 1D441/M2 equals 101, 325 kgm slash S2M2 equals 101, 325 kgm S2 letter 1D45D equals 760 mm times 1 m 1000 mm times 13. 6 g 1 cm 3 times 1 kg 1000 g times 100 cm 3 1 m 3 times 9. 81 m 1s 2 equals 0. 760 m 13 600 kg slash m3 9. 81 m slash s2 equals 1. 0 1 times 105 kg slash ms2 equals 1. 0, 1 times 105 letter 1d441 slash m2 equals 1. Check your learning. Calculate the height of a column of water at 25 degrees C that corresponds to normal atmospheric pressure. The density of water at this temperature is 1 g/cm3. Answer: 10.3 m. A manometer is a device similar to a barometer that can be used to measure the pressure of a gas trapped in a container. A closed-end manometer is a U-shaped tube with one closed arm, one arm that connects to the gas to be measured, and a non-volatile liquid, usually mercury, in between. As with a barometer, the distance between the liquid levels in the two arms of the tube, H in the diagram, is proportional to the pressure of the gas in the container. An open-end manometer, figure 9.5, is the same as a closed-end manometer, but one of its arms is open to the atmosphere. In this case, the distance between the liquid levels corresponds to the difference in pressure between the gas in the container and the atmosphere. 3 diagrams of manometers are shown. Each manometer consists of a spherical pink container filled with gas on the left that is connected to a U-shaped, sealed tube by a valve on its right. The top of the U aligns with the gas-filled sphere, and the U, which extends below, contains mercury. The first manometer has a sealed tube. The sealed end to the upper right in the diagram is labeled closed end and vacuum. The mercury level is higher in the right side of the tube than in the left. The difference in height is labeled H. Beneath this manometer illustration appears the label P subscript gas equal sign H rho G. The second manometer has an open-ended tube, which is labeled open end. At this opening in the upper right of the diagram is the label P subscript ATM. The mercury level is higher in the left side of the tube than in the right. This difference in height is labeled H. Beneath this manometer illustration appears the label P subscript gas equal sign P subscript ATM minus sign H rho G. The third manometer has an open-ended tube and is similar to the second manometer, except that the mercury level is higher in the right side of the tube than in the left. The difference in height is labeled H. Beneath this manometer illustration appears the label P subscript gas equal sign H rho G. The second manometer has an open-ended tube, which is labeled open end. At this opening in the upper right of the diagram is the label P subscript ATM. The mercury level is higher in the left side of the tube than in the right. This difference in height is labeled H. Beneath this manometer illustration appears the label P subscript gas equal sign P subscript ATM minus sign H rho G. The third manometer has an open-ended tube and is similar to the second manometer, except that the mercury level is higher in the right side of the tube than in the left. This difference in height is labeled H. Beneath this manometer illustration appears the label P subscript gas equal sign P subscript a Tm plus H rho G figure 9.5. A manometer can be used to measure the pressure of a gas. The difference in height between the liquid levels, H, is a measure of the pressure. Mercury is usually used because of its large density. Example 9.3. Calculation of pressure using a closed-end manometer. The pressure of a sample of gas is measured with a closed-end manometer, as shown to the right. The liquid in the manometer is mercury. Determine the pressure of the gas in A tor B pa C bar. A diagram of a closed-end manometer is shown. To the upper left is a spherical container labeled gas. This container is connected by a valve to a U-shaped tube which is labeled closed end at the upper right end. The container and a portion of tube that follows are shaded pink. The lower portion of the U-shaped tube is shaded gray, with the height of the gray region being greater on the right side than on the left. The difference in height between the left side and right side is 26. 4 cm, which is indicated with horizontal line segments and arrows. Solution: the pressure of the gas is equal to a column of mercury of height 26. 4 cm. The pressure at the bottom horizontal line is equal on both sides of the tube. The pressure on the left is due to the gas, and the pressure on the right is due to 26. 4 cm Hg, or mercury. We could use the equation P equals H rho G as in example 9.2, but it is simpler to just convert between units using table 9.1, A, 26. 4 cm Hg times 10 mm Hg, 1 cm Hg times 1 torr 1 Hg equals 264 torr. B. 264 torr times 1 atm 760 torr times 101. 325 pa 1 atm equals 35, 200 pa c. 35, 200 pa times 1 bar 100, 000 pa equals 0. 352 bar check. You're learning the pressure of a sample of gas is measured with a closed-end manometer. The liquid in the manometer is mercury. Determine the pressure of the gas in A torr B pa C bar. A diagram of a closed-end manometer is shown. To the upper left is a spherical container labeled gas. This container is connected by a valve to a U-shaped tube which is labeled closed end at the upper right end. The container and a portion of tube that follows are shaded pink. The lower portion of the U-shaped tube is shaded gray, with the height of the gray region being greater on the right side than on the left. The difference in height of 6. IN is indicated with horizontal line segments and arrows. Answer: A torr, B, pa, C tilde 0. 20 bar. Example 9. For calculation of pressure using an open-end manometer, the pressure of a sample of gas is measured at sea level with an open-end Hg, mercury manometer, as shown to the right. Determine the pressure of the gas in AIM Hg B, ATM C, Kpa. A diagram of an opni-end manometer is shown. To the upper left is a spherical container labeled gas. This container is connected by a valve to a U-shaped tube which is labeled open end at the upper right end. The container and a portion of tube that follows are shaded pink. The lower portion of the U-shaped tube is shaded gray, with the height of the gray region being greater on the right side than on the left. The difference in height of 13. 7 cm is indicated with horizontal line segments and arrows. Solution: the pressure of the gas equals the hydrostatic pressure due to a column of mercury of height 13. 7 cm plus the pressure of the atmosphere at sea level. The pressure at the bottom horizontal line is equal on both sides of the tube. The pressure on the left is due to the gas, and the pressure on the right is due to 13. 7 cm of Hg plus atmospheric pressure. A in Hg, this is 137 Hg plus 760 Hg equals 897 Hg. B, 897 Hg times 1 atm 760 Hg equals 1. 18 atm C, 1. 18 atm times 101. 325 K pa 1 atm equals 1. 20 times 102 K pa check. You're learning the pressure of a sample of gas is measured at sea level with an open-end Hg manometer, as shown to the right. Determine the pressure of the gas in AIM Hg B, ATM C, Kpa. A diagram of an open-end manometer is shown. To the upper left is a spherical container labeled gas. This container is connected by a valve to a U-shaped tube which is labeled open end at the upper right end. The container and a portion of tube that follows are shaded pink. The lower portion of the U-shaped tube is shaded gray, with the height of the gray region being greater on the left side than on the right. The difference in height of 4. 63 IN is indicated with horizontal line segments and arrows. Answer: A 642 Hg, B 0845 atm, C 85. 6 Kpa. Chemistry in everyday life. Measuring blood pressure is measured using a device called a sphygmomanometer, Greek sphygmos equals pulse. It consists of an inflatable cuff to restrict blood flow, a manometer to measure the pressure, and a method of determining when blood flow begins and when it becomes impeded. Figure 9.6. Since its invention in 1881, it has been an essential medical device. There are many types of sphygmomanometers, manual ones that require a stethoscope and are used by medical professionals, mercury ones used when the most accuracy is required, less accurate mechanical ones, and digital ones that can be used with little training but that have limitations. When using a sphygmomanometer, the cuff is placed around the upper arm and inflated until blood flow is completely blocked, then slowly released. As the heart beats, blood forced through the arteries causes a rise in pressure. This rise in pressure at which blood flow begins is the systolic pressure, the peak pressure in the cardiac cycle. When the cuff's pressure equals the arterial systolic pressure, blood flows past the cuff, creating audible sounds that can be heard using a stethoscope. This is followed by a decrease in pressure as the heart's ventricles prepare for another beat. As cuff pressure continues to decrease, eventually sound is no longer heard. This is the diastolic pressure, the lowest pressure, resting phase in the cardiac cycle. Blood pressure units from a sphygmomanometer are in terms of millimeters of mercury, Hg. This figure includes two photographs. The first photo shows a young adult male placing a blood pressure cuff on the upper arm of a young adult female. The second image shows a typical sphygmomanometer, which includes a black blood pressure cuff, tubing, pump, and pressure gauge. Figure 9.6. A medical technician prepares to measure a patient's blood pressure with a sphygmomanometer. B. A typical sphygmomanometer uses a valved rubber bulb to inflate the cuff and a diaphragm gauge to measure pressure. Credit a modification of work by Master SGT. Jeffrey Allen, How Sciences Interconnect Meteorology, Climatology, and Atmospheric Science Throughout the Ages. People have observed clouds, winds, and precipitation, trying to discern patterns and make predictions. When it is best to plant and harvest, whether it is safe to set out on a sea voyage, and much more. We now face complex weather and atmosphere-related challenges that will have a major impact on our civilization and the ecosystem. Several different scientific disciplines use chemical principles to help us better understand weather, the atmosphere, and climate. These are meteorology, climatology, and atmospheric science. Meteorology is the study of the atmosphere, atmospheric phenomena, and atmospheric effects on Earth's weather. Meteorologists seek to understand and predict the weather in the short term, which can save lives and benefit the economy. Weather forecasts, Figure 9.7, are the result of thousands of measurements of air pressure, temperature, and the like, which are compiled, modeled, and analyzed in weather centers worldwide. A weather map of the United States is shown, which points out areas of high and low pressure with the letters H in blue and L in red. Curved lines in gray, orange, blue, and red are shown. The orange lines are segmented. The red and blue lines have small red or blue semicircles and triangles attached along their lengths. In dashed white lines, latitude and longitude are indicated. Underlined 3- and 4-digit numbers also appear across the map. Figure 9. 7 meteorologists use weather maps to describe and predict weather. Regions of high H and low L pressure have large effects on weather conditions. The gray lines represent locations of constant pressure, known as isobars. Credit: modification of work by National Oceanic and Atmospheric Administration. In terms of weather, low-pressure systems occur when the Earth's surface atmospheric pressure is lower than the surrounding environment. Moist air rises and condenses, producing clouds. Movement of moisture and air within various weather fronts instigates most weather events. The atmosphere is the gaseous layer that surrounds a planet. Earth's atmosphere, which is roughly 100–125 km thick, consists of roughly 78.1% nitrogen and 21.0% oxygen, and can be subdivided further into the regions shown in Figure 9. 8. The exosphere furthest from Earth, 700 km above sea level, the thermosphere 8,700 km, the mesosphere 50–80 km, the stratosphere, second lowest level of our atmosphere, 1250 km above sea level, and the troposphere up to 12 km above sea level, roughly 80% of the Earth's atmosphere by mass and the layer where most weather events originate. As you go higher in the troposphere, air density and temperature both decrease. This diagram shows half of a two-dimensional view of the Earth in blue and green. A narrow white layer, labeled troposphere 0–12 km, covers this hemisphere. This layer is also labeled layer where most weather events originate. Next, a thicker light blue layer labeled stratosphere 12–50 km is shown. This is followed by a slightly thinner layer, also in light blue labeled mesosphere 50–80 km. Following this layer is a relatively thick light blue layer labeled thermosphere 80–700 km. A blue layer appears that covers the rightmost two-thirds of the diagram. This region gradually darkens from a lighter blue at the left to a dark blue at the right. This region of the diagram is labeled exosphere greater than 700 km. Figure 9.8 Earth's atmosphere has 5 layers: the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. Climatology is the study of the climate, averaged weather conditions over long time periods, using atmospheric data. However, climatologists study patterns and effects that occur over decades, centuries, and millennia, rather than shorter time frames of hours, days, and weeks like meteorologists. Atmospheric science is an even broader field, combining meteorology, climatology, and other scientific disciplines that study the atmosphere. Learning objectives: by the end of this section, you will be able to identify the mathematical relationships between the various properties of gases, use the ideal gas law, and related gas laws to compute the values of various gas properties under specified conditions during the 17th and especially 18th centuries. Driven both by a desire to understand nature and a quest to make balloons in which they could fly. Figure 9. 9. A number of scientists established the relationships between the macroscopic physical properties of gases, that is, pressure, volume, temperature, and amount of gas. Although their measurements were not precise by today's standards, they were able to determine the mathematical relationships between pairs of these variables, e.g., pressure and temperature, pressure and volume, that hold for an ideal gas, a hypothetical construct that real gases approximate under certain conditions. Eventually, these individual laws were combined into a single equation, the ideal gas law, that relates gas quantities for gases and is quite accurate for low pressures and moderate temperatures. We will consider the key developments in individual relationships, for pedagogical reasons not quite in historical order, then put them together in the ideal gas law. This figure includes 3 images. Image A is a black and white image of a hydrogen balloon apparently being deflated by a mob of people. In image B, a blue, gold, and red balloon is being held to the ground with ropes while positioned above a platform from which smoke is rising beneath the balloon. In C, an image is shown in gray on a peach-colored background of an inflated balloon with vertical striping in the air. It appears to have a basket attached to its lower side. A large stately building appears in the background. Figure 9. 9 in 1783, the first A. hydrogen-filled balloon flight, B. manned hot air balloon flight, and C. manned hydrogen-filled balloon flight occurred. When the hydrogen-filled balloon depicted in A. landed, the frightened villagers of Ganes reportedly destroyed it with pitchforks and knives. The launch of the latter was reportedly viewed by 400,000 people in Paris. Pressure and temperature. Amontons's law: imagine filling a rigid container attached to a pressure gauge with gas, and then sealing the container so that no gas may escape. If the container is cooled, the gas inside likewise gets colder, and its pressure is observed to decrease. Since the container is rigid and tightly sealed, both the volume and number of moles of gas remain constant. If we heat the sphere, the gas inside gets hotter, figure 9.10, and the pressure increases. This figure includes 3 similar diagrams. In the first diagram to the left, a rigid spherical container of a gas to which a pressure gauge is attached at the top is placed in a large beaker of water, indicated in light blue, atop a hot plate. The needle on the pressure gauge points to the far left on the gauge. The diagram is labeled low P above and hot plate off below. The second similar diagram also has the rigid spherical container of gas placed in a large beaker from which light blue wavy line segments extend from the top of the liquid in the beaker. The beaker is situated on top of a slightly reddened circular area. The needle on the pressure gauge points straight up or to the middle on the gauge. The diagram is labeled medium P above and hot plate on medium below. The third diagram also has the rigid spherical container of gas placed in a large beaker, in which bubbles appear near the liquid surface, and several wavy light blue line segments extend from the surface out of the beaker. The beaker is situated on top of a bright red circular area. The needle on the pressure gauge points to the far right on the gauge. The diagram is labeled high P above and hot plate on high below. Figure 9. 10. The effect of temperature on gas pressure. When the hot plate is off, the pressure of the gas in the sphere is relatively low. As the gas is heated, the pressure of the gas in the sphere increases. This relationship between temperature and pressure is observed for any sample of gas confined to a constant volume. An example of experimental pressure-temperature data is shown for a sample of air under these conditions in Figure 9. 11. We find that temperature and pressure are linearly related, and if the temperature is on the Kelvin scale, then P and T are directly proportional, again, when volume and moles of gas are held constant. If the temperature on the Kelvin scale increases by a certain factor, the gas pressure increases by the same factor. This figure includes a table and a graph. The table has 3 columns and 7 rows. The first row is a header, which labels the columns temperature degrees C, temperature K, and pressure kPa. The first column contains the following values from top to bottom: -100, -50, 0, 50, 100, and 150. The second column contains the values from top to bottom: 173, 223, 273, 323, 373, and 423. The third column contains the values 36.0, 46.4, 56.7, 67.1, 77.5, and 88.0. A graph appears to the right of the table. The horizontal axis is labeled temperature, K, with markings and labels provided for multiples of 100 beginning at 0 and ending at 500. The vertical axis is labeled pressure, kPa, with markings and labels provided for multiples of 10, beginning at 0 and ending at 100. 6 data points from the table are plotted on the graph with black dots. These dots are connected with a solid black line. A dashed line extends from the data point furthest to the left to the origin. The graph shows a positive linear trend. Figure 9. 11. For a constant volume and amount of air, the pressure and temperature are directly proportional, provided the temperature is in Kelvin. Measurements cannot be made at lower temperatures because of the condensation of the gas. When this line is extrapolated to lower pressures, it reaches a pressure of 0 at 273 degrees C, which is 0 on the Kelvin scale and the lowest possible temperature, called absolute zero. Guillaume Amontons was the first to empirically establish the relationship between the pressure and the temperature of a gas, ~1700, and Joseph Louis Gay-Lussac determined the relationship more precisely, ~1800. Because of this, the PT relationship for gases is known as either Amontons's law or Gay-Lussac's law. Under either name, it states that the pressure of a given amount of gas is directly proportional to its temperature on the Kelvin scale when the volume is held constant. Mathematically, this can be written: letter 1d443 proportional to letter 1d447 OR letter 1d443 equals constant times letter 1d447 OR letter 1d443 equals letter 1d458 times letter 1d447, where proportional to means is proportional to. And K is a proportionality constant that depends on the identity, amount, and volume of the gas. For a confined, constant volume of gas, the ratio PT is therefore constant, i.e., letter 1d443 letter 1d447 equals letter 1d458. If the gas is initially in condition 1, with P equals P1 and T equals T1, and then changes to condition 2, with P equals P2 and T equals T2, we have that letter 1d443, 1 letter 1d447, 1 equals letter 1d458, and P to letter 1d447, 2 equals letter 1d458, which reduces to letter 1d443, 1 letter 1d447, 1 equals letter 1d443 to T2. This equation is useful for pressure-temperature calculations for a confined gas at constant volume. Note that temperatures must be on the Kelvin scale for any gas law calculations, 0 on the Kelvin scale, and the lowest possible temperature is called absolute zero. Also note that there are at least 3 ways we can describe how the pressure of a gas changes as its temperature changes. We can use a table of values, a graph, or a mathematical equation. Example 9. 5 predicting change in pressure with temperature. A can of hairspray is used until it is empty, except for the propellant, isobutane gas. A, on the can is the warning: store only at temperatures below 120 degrees F, 48, 8 degrees C, do not incinerate. Y. B, the gas in the can is initially at 24 degrees C and 360 kPa, and the can has a volume of 350 ml. If the can is left in a car that reaches 50 degrees C on a hot day, what is the new pressure in the can? Solution: A. The can contains an amount of isobutane gas at a constant volume, so if the temperature is increased by heating, the pressure will increase proportionately. High temperature could lead to high pressure, causing the can to burst. Also, isobutane is combustible, so incineration could cause the can to explode. B. We are looking for a pressure change due to a temperature change at constant volume, so we will use Amontans's/Gay-Lussac's law, taking P1 and T1 as the initial values, T2 as the temperature where the pressure is unknown, and P2 as the unknown pressure. And converting degrees C to K, we have letter 1d443, 1 letter 1d447, 1 equals letter 1d443 to T, to which means that 360 K Pa 297, K equals letter 1d443, 2323, K rearranging and solving gives. Letter 1d443 2 equals 360 K Pa times 323, K 297, K equals 390 K Pa. Check, you're learning a sample of nitrogen. N2 occupies 45.0 ml at 27 degrees C and 600 torr. What pressure will it have if cooled to 73 degrees C while the volume remains constant? Answer: 400 torr volume and temperature. Charles's law: if we fill a balloon with air and seal it, the balloon contains a specific amount of air at atmospheric pressure, let's say 1 atm. If we put the balloon in a refrigerator, the gas inside gets cold and the balloon shrinks, although both the amount of gas and its pressure remain constant. If we make the balloon very cold, it will shrink a great deal, and it expands again when it warms up. Link to learning this video shows how cooling and heating a gas causes its volume to decrease or increase, respectively. These examples of the effect of temperature on the volume of a given amount of a confined gas at constant pressure are true in general. The volume increases as the temperature increases and decreases as the temperature decreases. Volume temperature data for a 1 mole sample of methane gas at 1 atm are listed and graphed in Figure 912. This figure includes a table and a graph. The table has 3 columns and 6 rows. The first row is a header, which labels the columns temperature degrees C, temperature K, and pressure kPa. The first column contains the values from top to bottom: -100, -50, 0, 100, and 200. The second column contains the values from top to bottom: 173, 223, 273, 373, and 473. The third column contains the values 14, 10, 18, 26, 22, 40, 30, 65, and 38, 88. A graph appears to the right of the table. The horizontal axis is labeled temperature, K, with markings and labels provided for multiples of 100 beginning at 0 and ending at 300. The vertical axis is labeled volume, L, with marking and labels provided for multiples of 10, beginning at 0 and ending at 30. 5 data points from the table are plotted on the graph with black dots. These dots are connected with a solid black line. The graph shows a positive linear trend. Figure 9. 12. The volume and temperature are linearly related for 1 mole of methane gas at a constant pressure of 1 atm. If the temperature is in Kelvin, volume and temperature are directly proportional. The line stops at 111 K because methane liquefies at this temperature. When extrapolated, it intersects the graph's origin, representing a temperature of absolute 0. The relationship between the volume and temperature of a given amount of gas at constant pressure is known as Charles's law in recognition of the French scientist and balloon flight pioneer Jacques-Alexandre César Charles. Charles's law states that the volume of a given amount of gas is directly proportional to its temperature on the Kelvin scale when the pressure is held constant. Mathematically, this can be written as letter 1d449 alpha, letter 1d447 OR letter 1d449 equals constant letter 1d447 OR letter 1d449 equals letter 1d458 letter 1d447 OR letter 1d449. 1/letter 1d4471 equals letter 1d4492 / letter 1d4472, with K being a proportionality constant. that depends on the amount and pressure of the gas. For a confined, constant pressure gas sample, Vt is constant, i.e., the ratio equals K. And as seen with the PT relationship, this leads to another form of Charles's law. Letter 1d4491 letter 1d4471 equals letter 1d449 to T2. Example 9. 6. Predicting change in volume with temperature A sample of carbon dioxide, CO2, occupies 0. 300 L at 10 degrees C and 750 torr. What volume will the gas have at 30 degrees C and 750 torr? Solution: because we are looking for the volume change caused by a temperature change at constant pressure, this is a job for Charles's law. Taking V1 and T1 as the initial values, T2 as the temperature at which the volume is unknown, and V2 as the unknown volume, and converting degrees C into K, we have letter 1d449 1 letter 1d447 1 equals letter 1d449 to T, which means that 0. 300 L 283 K equals letter 1d449 2303 K. Rearranging and solving gives letter 1d449 2 equals 0. 300 L times 303 K 283 K equals 0. 321 L. This answer supports our expectation from Charles's law, namely, that raising the gas temperature from 283 K to 303 K at a constant pressure will yield an increase in its volume from 0. 300 L to 0. 321 L. Check your learning. A sample of oxygen, O2, occupies 32 ml at 30 degrees C and 452 torr. What volume will it occupy at 70 degrees C and the same pressure? Answer: 21. 6 ml. Example 9. 7. Measuring temperature with a volume change. Temperature is sometimes measured with a gas thermometer by observing the change in the volume of the gas as the temperature changes at constant pressure. The hydrogen in a particular hydrogen gas thermometer has a volume of 150 cm3 when immersed in a mixture of ice and water, 0 C. When immersed in boiling liquid ammonia, the volume of the hydrogen at the same pressure is 131 7 cm3. Find the temperature of boiling ammonia on the Kelvin and Celsius scales. Solution: when immersed in an ice water bath at 0 C T1, the thermometer's gas volume is 150 cm3 V1. When immersed in boiling liquid ammonia, T2, the thermometer's gas volume is 131 7 cm3. The relation between volume and temperature at constant pressure is provided by Charles's law. Letter 1d449 1 letter 1d447 1 equals letter 1d449 to T, which means that 150 cm 15K equals 131 7 cm3. Letter 1d4472 rearrangement gives letter 1d4472 equals 131 7 cm3 times 273 15K 150 0 cm3 equals 239 8K. Subtracting 273 15 from 239 8K, we find that the temperature of the boiling ammonia on the Celsius scale is 33.4 degrees C. Check your learning. What is the volume of a sample of ethane at 467 K and 1 atm if it occupies 405 ml at 298 K and 1 atm? Answer: 635 ml. Volume and pressure. Boyle's law: if we partially fill an airtight syringe with air, the syringe contains a specific amount of air at constant temperature, say 25 degrees C. If we slowly push in the plunger while keeping temperature constant, the gas in the syringe is compressed into a smaller volume and its pressure increases. If we pull out the plunger, the volume increases and the pressure decreases. This example of the effect of volume on the pressure of a given amount of a confined gas is true in general. Decreasing the volume of a contained gas will increase its pressure, and increasing its volume will decrease its pressure. In fact, if the volume increases by a certain factor, the pressure decreases by the same factor, and vice versa. Volume pressure data for an air sample at room temperature are graphed in Figure 913. This figure contains a diagram and two graphs. The diagram shows a syringe labeled with a scale in ml or cc, with multiples of 5 labeled beginning at 5 and ending at 30. The markings halfway between these measurements are also provided. Attached at the top of the syringe is a pressure gauge with a scale marked by 5s from 40 on the left to 5 on the right. The gauge needle rests between 10 and 15, slightly closer to 15. The syringe plunger position indicates a volume measurement about halfway between 10 and 15 ml or cc. The first graph is labeled V ml on the horizontal axis and P psi on the vertical axis. Points are labeled at 5, 10, 15, 20, and 25 ml with corresponding values of 39, 0, 19.5, 13.0, 9.8, and 6.5 psi. The points are connected with a smooth curve that is declining at a decreasing rate of change. The second graph is labeled V ml on the horizontal axis and 1 divided by P psi on the vertical axis. The horizontal axis is labeled at multiples of 5, beginning at 0 and extending up to 35 ml. The vertical axis is labeled by multiples of 0.2, beginning at 0 and extending up to 0. 18. 6 points indicated by black dots on this graph are connected with a black line segment showing a positive linear trend. Figure 9. 13. When a gas occupies a smaller volume, it exerts a higher pressure. When it occupies a larger volume, it exerts a lower pressure, assuming the amount of gas and the temperature do not change. Since P and V are inversely proportional, a graph of 1P versus V is linear. Unlike the PT and VT relationships, pressure and volume are not directly proportional to each other. Instead, P and V exhibit inverse proportionality. Increasing the pressure results in a decrease of the volume of the gas. Mathematically, this can be written with K being a constant. Graphically, this relationship is shown by the straight line that results when plotting the inverse of the pressure, 1P versus the volume V, or the inverse of volume, 1V, versus the pressure P. Graphs with curved lines are difficult to read accurately at low or high values of the variables, and they are more difficult to use in fitting theoretical equations and parameters to experimental data. For those reasons, scientists often try to find a way to linearize their data. If we plot P versus V, we obtain a hyperbola. See Figure 9. 14. This diagram shows two graphs. In a graph is shown with volume on the horizontal axis and pressure on the vertical axis. A curved line is shown on the graph, showing a decreasing trend with a decreasing rate of change. In B, a graph is shown with volume on the horizontal axis and 1 divided by pressure on the vertical axis. A line segment, beginning at the origin of the graph, shows a positive linear trend. Figure 9. 14. The relationship between pressure and volume is inversely proportional. A, the graph of P versus V is a hyperbola, whereas B, the graph of 1P versus V is linear. The relationship between the volume and pressure of a given amount of gas at constant temperature was first published by the English natural philosopher Robert Boyle over 300 years ago. It is summarized in the statement now known as Boyle's law. The volume of a given amount of gas held at constant temperature is inversely proportional to the pressure under which it is measured. Example 9. 8 volume of a gas sample. The sample of gas in Figure 9.13 has a volume of 15, 0 ml at a pressure of 13, 0 psi. Determine the pressure of the gas at a volume of 7.5 ml using A, the PV graph in Figure 9.13, B, the 1P versus V graph in Figure 9.13, C, the Boyle's law equation. Comment on the likely accuracy of each method. Solution A, estimating from the PV graph, gives a value for P somewhere around 27 psi. B, estimating from the 1P versus V graph, give a value of about 26 psi. C, from Boyle's law, we know that the product of pressure and volume, PV, for a given sample of gas at a constant temperature is always equal to the same value. Therefore, we have P1V1 equals K and P to V2 equals K, which means that P1V1 equals P to V2. Using P1 and V1 as the known values 13, 0 psi and 15, 0 ml, P2 as the pressure at which the volume is unknown, and V2 as the unknown volume, we have Letter 1 D443 1 letter 1 D449 1 equals letter 1 D443 to Vitor 13. 0 psi times 15. 0 ml equals letter 1 D4432 2 times 7. 5 ml solving, letter 1 D4432 equals 13. 0 psi times 15. 0 ml 7. 5 ml equals 26 psi. It was more difficult to estimate well from the PV graph, so A is likely more inaccurate than B or C. The calculation will be as accurate as the equation and measurements allow. Check your learning. The sample of gas in figure 913 has a volume of 30. 0 ml at a pressure of 6.5 psi. Determine the volume of the gas at a pressure of 11. 0 psi using A. The PV graph in figure 913, B. The 1P versus V graph in figure 913, C. The Boyle's law equation. Comment on the likely accuracy of each method. Answer: A. About 17-18 ml. B. ml. C. 17.7 ml. It was more difficult to estimate well from the PV graph, so A is likely more inaccurate than B. The calculation will be as accurate as the equation and measurements allow. Chemistry, in everyday life. Breathing, and Boyle's law. What do you do about 20 times per minute for your whole life, without break, and often without even being aware of it? The answer, of course, is respiration or breathing. How does it work? It turns out that the gas laws apply here. Your lungs take in gas that your body needs, oxygen, and get rid of waste gas, carbon dioxide. Lungs are made of spongy, stretchy tissue that expands and contracts while you breathe. When you inhale, your diaphragm and intercostal muscles, the muscles between your ribs, contract, expanding your chest cavity and making your lung volume larger. The increase in volume leads to a decrease in pressure, Boyle's law. This causes air to flow into the lungs from high pressure to low pressure. When you exhale, the process reverses. Your diaphragm and rib muscles relax, your chest cavity contracts, and your lung volume decreases, causing the pressure to increase, Boyle's law again, and air flows out of the lungs from high pressure to low pressure. You then breathe in and out again, and again, repeating this Boyle's law cycle for the rest of your life. Figure 915. This figure contains two diagrams of a cross-section of the human head and torso. The first diagram on the left is labeled inspiration. It shows curved arrows in gray proceeding through the nasal passages and mouth to the lungs. An arrow points downward from the diaphragm, which is relatively flat just beneath the lungs. This arrow is labeled diaphragm contracts. At the entrance to the mouth and nasal passages, a label of P subscript lungs equals 1-3 torr lower is provided. The second, similar diagram, which is labeled expiration, reverses the direction of both arrows. Arrows extend from the lungs out through the nasal passages and mouth. Similarly, an arrow points up to the diaphragm, showing a curved diaphragm and lungs reduced in size from the previous image. This arrow is labeled diaphragm relaxes. At the entrance to the mouth and nasal passages, a label of P subscript lungs equals 1-3 torr higher is provided. Figure 915 breathing occurs because expanding and contracting lung volume creates small pressure differences between your lungs and your surroundings, causing air to be drawn into and forced out of your lungs. Moles of gas and volume. Avogadro's law. The Italian scientist Amedeo Avogadro advanced a hypothesis in 1811 to account for the behavior of gases, stating that equal volumes of all gases, measured under the same conditions of temperature and pressure, contain the same number of molecules. Over time, this relationship was supported by many experimental observations as expressed by Avogadro's law. For a confined gas, the volume, V, and number of moles, N, are directly proportional if the pressure and temperature both remain constant. In equation form, this is written as letter 1 D449 proportional to letter 1 D45B, OR letter 1 D449, equals letter 1 D458 times letter 1 D45B, OR letter 1 D449. 1 letter 1 D45B 1 equals letter 1 D449 to N2. Mathematical relationships can also be determined for the other variable pairs, such as P versus N and N versus T. Link to learning. Visit this interactive pH-ET simulation to investigate the relationships between pressure, volume, temperature, and amount of gas. Use the simulation to examine the effect of changing one parameter on another while holding the other parameters constant, as described in the preceding sections on the various gas laws. The ideal gas law. To this point, 4 separate laws have been discussed that relate pressure, volume, temperature, and the number of moles of the gas. Boyle's law, PV equals constant at constant T and N. Amonton's law, PT equals constant at constant V and N. Charles's law, Vt equals constant at constant P and N. Avogadro's law, letter 1d449 letter 1d45b, equals constant at constant P and T. Combining these 4 laws yields the ideal gas law, a relation between the pressure, volume, temperature, and number of moles of a gas. Letter 1d443 letter 1d449 equals letter 1d45b, letter 1d445 letter 1d447. Where P is the pressure of a gas, V is its volume, N is the number of moles of the gas, T is its temperature on the Kelvin scale, and R is a constant called the ideal gas constant or the universal gas constant. The units used to express pressure, volume, and temperature will determine the proper form of the gas constant as required by dimensional analysis, the most commonly encountered values being 0, 8,206 LATM mol 1 K1 and 8, 314 kPa L mol 1 K1. Gases whose properties of P, V, and T are accurately described by the ideal gas law, or the other gas laws, are said to exhibit ideal behavior or to approximate the traits of an ideal gas. An ideal gas is a hypothetical construct that may be used along with kinetic molecular theory to effectively explain the gas laws, as will be described in a later module of this chapter. Although all the calculations presented in this module assume ideal behavior, this assumption is only reasonable for gases under conditions of relatively low pressure and high temperature. In the final module of this chapter, a modified gas law will be introduced that accounts for the non-ideal behavior observed for many gases at relatively high pressures and low temperatures. The ideal gas equation contains 5 terms: the gas constant R and the variable properties P, V, N, and T specifying any 4 of these terms will permit use of the ideal gas law to calculate the 5th term as demonstrated in the following example exercises. Example 9. Using the ideal gas law, methane, CH4, is being considered for use as an alternative automotive fuel to replace gasoline. 1 gallon of gasoline could be replaced by 655 g of CH4. What is the volume of this much methane at 25 degrees C and 745 torr? Solution. We must rearrange PV equals nRT to solve for V. Letter 1d449 equals letter 1d45b, letter 1d445, letter 1d447, letter 1d443. If we choose to use R equals 0, 8,206 LATM mol 1 K1, then the amount must be in moles, temperature must be in Kelvin, and pressure must be in ATM. Converting into the right units, letter 1d45b equals 655 GCH, 4 times 1 mol, 16. 43 GCH4 equals 40. 8 mol. Letter 1d447 equals 25 degrees C plus 273 equals 298 K. Letter 1d443 equals 745 torr times 1 ATM 760 torr equals 0, 980 ATM. Letter 1d449 equals letter 1d45b, letter 1d445, letter 1d447, letter 1d443 equals 40. 8 mol. 0. 08206 latam mol 1 K1, 298 K 0. 980 ATM equals 1. 0 2 times 103 L. It would require 1020 L, 269 gal, of gaseous methane at about 1 ATM of pressure to replace 1 gal of gasoline. It requires a large container to hold enough methane at 1 ATM to replace several gallons of gasoline. Check your learning. Calculate the pressure in bar of 2520 moles of hydrogen gas stored at 27 degrees C in the 180 L storage tank of a modern hydrogen-powered car. Answer: 350 bar. If the number of moles of an ideal gas are kept constant under 2 different sets of conditions, a useful mathematical relationship called the combined gas law is obtained. Letter 1 D443, 1 letter 1 D449, 1 letter 1 D447. 1 equals letter 1 D443 to V to T2. Using units of ATM, L, and K. Both sets of conditions are equal to the product of N times R, where N equals the number of moles of the gas, and R is the ideal gas law constant. Example 9. 10. Using the combined gas law. When filled with air, a typical scuba tank with a volume of 13. 2L has a pressure of 153 atm, figure 916. If the water temperature is 27 degrees C, how many liters of air will such a tank provide to a diver's lungs at a depth of approximately 70 feet in the ocean where the pressure is 313 atm? This photograph shows a scuba diver underwater with a tank on his or her back and bubbles ascending from the breathing apparatus. Figure 9. 16 scuba divers use compressed air to breathe while underwater. Credit. Modification of work by Mark Goodchild. Solution. Letting 1 represent the air in the scuba tank and 2 represent the air in the lungs, and noting that body temperature, the temperature the air will be in the lungs, is 37 degrees C, we have letter 1 D443, 1 letter 1 D449, 1 letter 1 D447, 1 equals letter 1 D443 to V to letter 1 D447, 2, 153 atm. 13. 2L, 300K equals 3. 13 atm, letter 1 D4492, 310K. Solving for V2, letter 1 D4492 equals 153 atm. 13. 2L, 310K, 300K, 3. 13 atm equals 667L. Note, be advised that this particular example is one in which the assumption of ideal gas behavior is not very reasonable, since it involves gases at relatively high pressures and low temperatures. Despite this limitation, the calculated volume can be viewed as a good ballpark estimate. Check your learning. A sample of ammonia is found to occupy 250 L under laboratory conditions of 27 degrees C and 850 atm. Find the volume of this sample at 0 degrees C and 10 atm. Answer: 193 L. Chemistry in everyday life. The interdependence between ocean depth and pressure in scuba diving. Whether scuba diving at the Great Barrier Reef in Australia, shown in Figure 9. 17, or in the Caribbean, divers must understand how pressure affects a number of issues related to their comfort and safety. This picture shows colorful underwater corals and anemones in hues of yellow, orange, green, and brown, surrounded by water that appears blue in color. Figure 9. 17 scuba divers, whether at the Great Barrier Reef or in the Caribbean, must be aware of buoyancy, pressure equalization, and the amount of time they spend underwater to avoid the risks associated with pressurized gases in the body. Credit Kyle Taylor. Pressure increases with ocean depth, and the pressure changes most rapidly as divers reach the surface. The pressure a diver experiences is the sum of all pressures above the diver, from the water and the air. Most pressure measurements are given in units of atmospheres, expressed as atmospheres absolute or ATA in the diving community. Every 33 feet of salt water represents 1 ATA of pressure, in addition to 1 ATA of pressure from the atmosphere at sea level. As a diver descends, the increase in pressure causes the body's air pockets in the ears and lungs to compress. On the ascent, the decrease in pressure causes these air pockets to expand, potentially rupturing eardrums or bursting the lungs. Divers must therefore undergo equalization by adding air to body air spaces on the descent by breathing normally, and adding air to the mask by breathing out of the nose or adding air to the ears and sinuses by equalization techniques. The corollary is also true on ascent. Divers must release air from the body to maintain equalization. Buoyancy, or the ability to control whether a diver sinks or floats, is controlled by the buoyancy compensator, BCD. If a diver is ascending, the air in their BCD expands because of lower pressure according to Boyle's law. Decreasing the pressure of gases increases the volume. The expanding air increases the buoyancy of the diver, and they begin to ascend. The diver must vent air from the BCD or risk an uncontrolled ascent that could rupture the lungs. In descending, the increased pressure causes the air in the BCD to compress, and the diver sinks much more quickly. The diver must add air to the BCD or risk an uncontrolled descent, facing much higher pressures near the ocean floor. The pressure also impacts how long a diver can stay underwater before ascending. The deeper a diver dives, the more compressed the air that is breathed because of increased pressure. If a diver dives 33 feet, the pressure is 2 ATA, and the air would be compressed to 1/2 of its original volume. The diver uses up available air twice as fast as at the surface. Standard conditions of temperature and pressure. We have seen that the volume of a given quantity of gas and the number of molecules, moles, in a given volume of gas vary with changes in pressure and temperature. Chemists sometimes make comparisons against a standard temperature and pressure, SDP, for reporting properties of gases, 273 K and 1 atm, 101, 325 kPa. 1 at SDP, 1 mole of an ideal gas has a volume of about 22. 4L, this is referred to as the standard molar volume, figure 918. This figure shows 3 balloons each filled with He, NH subscript 2, and O subscript 2, respectively. Beneath the first balloon is the label 4G of He, beneath the second balloon is the label 17G of NH subscript 2. Beneath the third balloon is the label 32G of O subscript 2. Each balloon contains the same number of molecules of their respective gases, figure 918. Regardless of its chemical identity, 1 mole of gas behaving ideally occupies a volume of (22). 4L at SDP. Learning objectives. By the end of this section, you will be able to use the ideal gas law to compute gas densities and molar masses, perform stoichiometric calculations involving gaseous substances, state Dalton's law of partial pressures, and use it in calculations involving gaseous mixtures. The study of the chemical behavior of gases was part of the basis of perhaps the most fundamental chemical revolution in history. French nobleman Antoine Lavoisier, widely regarded as the father of modern chemistry, changed chemistry from a qualitative to a quantitative science through his work with gases. He discovered the law of conservation of matter, discovered the role of oxygen in combustion reactions, determined the composition of air, explained respiration in terms of chemical reactions, and more. He was a casualty of the French Revolution, guillotined in 1794. Of his death, mathematician and astronomer Joseph Louis Lagrange said, "It took the mob only a moment to remove his head. A century will not suffice to reproduce it." Too much of the knowledge we do have about Lavoisier's contributions is due to his wife, Marie-Anne Pauls Lavoisier, who worked with him in his lab. A trained artist fluent in several languages, she created detailed illustrations of the equipment in his lab and translated texts from foreign scientists to complement his knowledge. After his execution, she was instrumental in publishing Lavoisier's major treatise, which unified many concepts of chemistry and laid the groundwork for significant further study. As described in an earlier chapter of this text, we can turn to chemical stoichiometry for answers to many of the questions that ask, how much? The essential property involved in such use of stoichiometry is the amount of substance, typically measured in moles N. For gases, molar amount can be derived from convenient experimental measurements of pressure, temperature, and volume. Therefore, these measurements are useful in assessing the stoichiometry of pure gases, gas mixtures, and chemical reactions involving gases. This section will not introduce any new material or ideas, but will provide examples of applications and ways to integrate concepts already discussed. Gas density and molar mass. The ideal gas law described previously in this chapter relates the properties of pressure P, volume V, temperature T, and molar amount N. This law is universal, relating these properties in identical fashion regardless of the chemical identity of the gas. Letter 1D443, letter 1D449 equals letter 1D45B, letter 1D445, letter 1D447. The density D of a gas, on the other hand, is determined by its identity. As described in another chapter of this text, the density of a substance is a characteristic property that may be used to identify the substance. Letter 1D451 equals letter 1D45A, letter 1D449, rearranging the ideal gas equation to isolate V. and substituting into the density equation yields letter 1d451 equals letter 1d45a, letter 1d443, letter 1d45b, letter 1d445, letter 1d447 equals letter 1d45a, letter 1d45b, letter 1d443, letter 1d445, letter 1d447. The ratio, mn, is the definition of molar mass. M, letter 2133, equals letter 1d45a, letter 1d45b. The density equation can then be written letter 1d451 equals letter 2133, letter 1d443, letter 1d445, letter 1d447. This relation may be used for calculating the densities of gases of known identities at specified values of pressure and temperature, as demonstrated in example 9. 11. Example 9. 11. Measuring gas density. What is the density of molecular nitrogen gas at SDP? Solution: the molar mass of molecular nitrogen, N2, is 28, 1 g/mol. Substituting this value, along with standard temperature and pressure, into the gas density equation, yields letter 1d451 equals letter 2133, letter 1d443, letter 1d445, letter 1d447 equals 28, 0, 1 g/mol, 1, 0, 0 atm, 0, 0821 latm mol minus 1 k minus 1, 273 k equals 1. 25 gl. Check your learning. What is the density of molecular hydrogen gas at 17? 0 degrees C and a pressure of 760 torr. Answer: D equals 0. 847 gl. When the identity of a gas is unknown, measurements of the mass, pressure, volume, and temperature of a sample can be used to calculate the molar mass of the gas, a useful property for identification purposes. Combining the ideal gas equation and the definition of molar mass letter 2133 equals letter 1d45a, letter 1d45b, yields the following equation. Letter 2133 equals letter 1d45a, letter 1d445, letter 1d447, letter 1d443, letter 1d449. Determining the molar mass of a gas via this approach is demonstrated in example 9. 12. Example 9. 12. Determining the molecular formula of a gas from its molar mass and empirical formula. Cyclopropane, a gas once used with oxygen as a general anesthetic, is composed of 85.7% carbon and 14.3% hydrogen by mass. Find the empirical formula. If 156 g of cyclopropane occupies a volume of 1 L at 0, 984 atm and 50 degrees C, what is the molecular formula for cyclopropane? Solution: first determine the empirical formula of the gas. Assume 100 g and convert the percentage of each element into grams. Determine the number of moles of carbon and hydrogen in the 100 g sample of cyclopropane. Divide by the smallest number of moles to relate the number of moles of carbon to the number of moles of hydrogen. In the last step, realize that the smallest whole number ratio is the empirical formula, 85. 7 gC times 1 mol C12, 1 gC equals 7, 136 mol C7, 1367, 136 equals 1, mol C14, 3 gH times 1 mol H1, 1 gH equals 14, 158 mol H, 14, 15, 87, 136 equals 1. 98 mol H. Empirical formula is CH2, empirical mass M of 14. 3 G empirical unit. Next, use the provided values for mass, pressure, temperature, and volume to compute the molar mass of the gas. Letter 2133 equals letter 1d45a, letter 1d445, letter 1d447, letter 1d443, letter 1d449 equals 1. 56 g, 0. 0821 latm mol minus 1 k minus 1, 323 k, 0. 984 atm, 1. L. 0 g/mol. Comparing the molar mass to the empirical formula mass shows how many empirical formula units make up a molecule. Letter 2133, letter 1d438, letter 1d440 equals 42. 0 g/mol 14. 0 g/mol equals 3. The molecular formula is thus derived from the empirical formula by multiplying each of its subscripts by 3. CH2, 3 equals C3H6. Check your learning. Acetylene, a fuel used in welding torches, is composed of 92.3% C and 77% H by mass. Find the empirical formula. If 110 g of acetylene occupies a volume of 1 L at 115 atm and 59.5 degrees C, what is the molecular formula for acetylene? Answer: empirical formula, CH. Molecular formula, C2H2. Example 9. 13. Determining the molar mass of a volatile liquid. The approximate molar mass of a volatile liquid can be determined by heating a sample of the liquid in a flask with a tiny hole at the top, which converts the liquid into gas that may escape through the hole, removing the flask from heat at the instant when the last bit of liquid becomes gas, at which time the flask will be filled with only gaseous sample at ambient pressure, sealing the flask and permitting the gaseous sample to condense to liquid, and then weighing the flask to determine the sample's mass. See Figure 9. 19. This figure shows 4 photos, each connected by a right-facing arrow. The first photo shows a glass flask with aluminum foil covering the top sitting on a scale. The second photo shows a syringe being inserted into the flask through the aluminum foil covering. The third photo shows the glass flask being inserted into a beaker of water. The water appears to be heated at 100. The fourth photo shows the glass flask being weighed again. Figure 9. 19. When the volatile liquid in the flask is heated past its boiling point, it becomes gas and drives air out of the flask. At letter 1D461, letter 1D459, letter 1D454, the flask is filled with volatile liquid gas at the same pressure as the atmosphere. If the flask is then cooled to room temperature, the gas condenses, and the mass of the gas that filled the flask and is now liquid can be measured. Credit: modification of work by Mark Ott, using this procedure. A sample of chloroform gas weighing 0.494 g is collected in a flask with a volume of 129 cm3 at 99.6 degrees C when the atmospheric pressure is 742.1 Hg. What is the approximate molar mass of chloroform? Solution: since letter 2133 equals letter 1D45A, letter 1D45B, and letter 1D45B equals letter 1D443, letter 1D449, letter 1D445, letter 1D447. Substituting and rearranging gives letter 2133 equals letter 1D45A, letter 1D445, letter 1D447, letter 1D443, letter 1D449. Then letter 2133 equals letter 1D45A, letter 1D445, letter 1D447, letter 1D443, letter 1D449 equals 0.494 g times 0.8206 LATM/mol K times 372, 8 K 0.976 ATM times 0.129 L equals 120 g/mol. Check your learning. A sample of phosphorus that weighs 3,243 times 10⁻² g exerts a pressure of 31.89 kPa in a 560 ml bulb at 550 degrees C. What are the molar mass and molecular formula of phosphorus vapor? Answer: 124 g/mol P for the pressure of a mixture of gases. Dalton's law: unless they chemically react with each other, the individual gases in a mixture of gases do not affect each other's pressure. Each individual gas in a mixture exerts the same pressure that it would exert if it were present alone in the container. Figure 920. The pressure exerted by each individual gas in a mixture is called its partial pressure. This observation is summarized by Dalton's law of partial pressures. The total pressure of a mixture of ideal gases is equal to the sum of the partial pressures of the component gases. Letter 1D443, letter 1D447, letter 1D45C, letter 1D461, letter 1D44, letter 1D459 equals letter 1D443, letter 1D434, plus letter 1D443, letter 1D435, plus letter 1D443, letter 1D436 plus equals sigma letter 1D443I. In the equation, P total is the total pressure of a mixture of gases. PA is the partial pressure of gas A. PB is the partial pressure of gas B. PC is the partial pressure of gas C, and so on. This figure includes images of 4 gas-filled cylinders or tanks. Each has a valve at the top. The interior of the first cylinder is shaded blue. This region contains 5 small blue circles that are evenly distributed. The label 300 kp is on the cylinder. The second cylinder is shaded lavender. This region contains 8 small purple circles that are evenly distributed. The label 450 kp is on the cylinder. To the right of these cylinders is a third cylinder. Its interior is shaded pale yellow. This region contains 12 small yellow circles that are evenly distributed. The label 6000 kp is on this region of the cylinder. An arrow labeled total pressure combined appears to the right of these 3 cylinders. This arrow points to a fourth cylinder. The interior of this cylinder is shaded a pale green. It contains evenly distributed small circles in the following quantities and colors: 5 blue, 8 purple, and 12 yellow. This cylinder is labeled 1350 kPa, figure 9. 20. If equal volume cylinders containing gases at pressures of 300 kPa, 450 kPa, and 600 kPa are all combined in the same size cylinder, the total pressure of the gas mixture is 1350 kPa. The partial pressure of gas A is related to the total pressure of the gas mixture via its mole fraction X. A unit of concentration defined as the number of moles of a component of a solution divided by the total number of moles of all components. Letter 1D443 letter 1D434 equals letter 1D44B letter 1D434 times letter 1D443 letter 1D447 letter 1D45C letter 1D461 letter 1D44 letter 1D459 where letter 1D44B letter 1D434 equals letter 1D45B letter 1D434 letter 1D45B letter 1D447 letter 1D45C letter 1D461 letter 1D44 letter, where PA, XA, and NA are the partial pressure, mole fraction, and number of moles of gas A, respectively, and N total is the number of moles of all components in the mixture. Example 9. 14. The pressure of a mixture of gases, a 10-0L vessel contains 2. 50 times 10 minus 3 mol of H2, 1 times 10 minus 3 mol of He, and 3 times 10 minus 4 mol of Ni at 35 degrees C. A. What are the partial pressures of each of the gases? B. What is the total pressure in atmospheres? Solution: the gases behave independently, so the partial pressure of each gas can be determined from the ideal gas equation. Using letter 1D443 equals letter 1D45B, letter 1D445, letter 1D447, letter 1D449. Letter 1D443H2 equals 2. 50 times 10 minus 3 mol, 0. Lat mol kk, 0 L equals 6. 32 times 10 minus 3 atm, letter 1D443He equals 1. 0 0 times 10 minus 3 mol, 0. Lat mol kk, 0 L equals 2. 53 times 10 minus 3 atm, letter 1D443Ne equals 3. 0 0 times 10 minus 4 mol, 0. Lat mol kk, 0 L equals 7. 58 times 10 minus 4 atm, the total pressure is given by the sum of the partial pressures. Letter 1D443T equals letter 1D443H2 plus letter 1D443He plus letter 1D443Ne equals 0. 632 plus 0. 253 plus 0. 00076 atm equals 9. 61 times 10 minus 3 atm check, you're learning a 5. 73 L flask at 25 degrees C contains 0. 388 mol of N2, 147 mol of Co, and 0803 mol of H2. What is the total pressure in the flask in atmospheres? Answer: 137 atm. Here is another example of this concept, but dealing with mole fraction calculations. Example 9. 15. The pressure of a mixture of gases, a gas mixture used for anesthesia, contains 283 mol oxygen, O2, and 841 mol nitrous oxide, N2O. The total pressure of the mixture is 192 kPa. A. What are the mole fractions of O2 and N2O? B. What are the partial pressures of O2 and N2O? Solution: the mole fraction is given by letter 1D44B, letter 1D434, equals letter 1D45B, letter 1D434, letter 1D45B, letter 1D447, letter 1D45C, letter 1D461, letter 1D44, letter 1D459. And the partial pressure is PA equals XA times P total. For O2, letter 1D44B, letter 1D442, 2 equals letter 1 D45B, letter 1 D442 to letter 1 D45B, letter 1 D447, letter 1 D45C, letter 1 D461, letter 1 D44, letter 1 D459 equals 2. 83 mol, 2. 83 plus 8. 41 mol equals 0. 252 and letter 1 D443, letter 1 D442, 2 equals letter 1 D44B, letter 1 D442, 2 times letter 1 D443, letter 1 D447, letter 1 D45C, letter 1 D461, letter 1 D44, letter 1 D459 equals 0. 252 times 192 kpa equals 48. 4 kpa for N2O, x centa letter 1 D442 equals letter 1 D45B, letter 1 D441 to letter 1 D442, letter 1 D45B, total equals 8. 41 mol 2. 83 plus 8. 41 mol equals 0. 748 and P to letter 1 D442 equals letter 1 D44B, letter 1 D441 to letter 1 D442 times letter 1 D443 total equals 0. 748 times 192 kpa equals 144 kpa. Check your learning. What is the pressure of a mixture of 0? 200 G of H2, 1. G of N2 and 0 820 G of R in a container with a volume of 2. L at 20 degrees C. Answer: 1. 87 atm collection of gases over water. A simple way to collect gases that do not react with water is to capture them in a bottle that has been filled with water and inverted into a dish filled with water. The pressure of the gas inside the bottle can be made equal to the air pressure outside by raising or lowering the bottle. When the water level is the same both inside and outside the bottle, figure 9. 21, the pressure of the gas is equal to the atmospheric pressure, which can be measured with a barometer. This figure shows a diagram of equipment used for collecting a gas over water. To the left is an Erlenmeyer flask. It is approximately 2/3 full of a lavender-colored liquid. Bubbles are evident in the liquid. The label reaction producing gas appears below the flask. A line segment connects this label to the liquid in the flask. The flask has a stopper in it through which a single glass tube extends from the open region above the liquid in the flask up, through the stopper, to the right, then angles down into a pan that is nearly full of light blue water. This tube again extends right once it is well beneath the water's surface. It then bends up into an inverted flask, which is labeled collection flask. This collection flask is positioned with its mouth beneath the surface of the light blue water and appears approximately half full. Bubbles are evident in the water in the inverted flask. The open space above the water in the inverted flask is labeled collected gas. Figure 9. 21. When a reaction produces a gas that is collected above water, the trapped gas is a mixture of the gas produced by the reaction and water vapor. If the collection flask is appropriately positioned to equalize the water levels both within and outside the flask, the pressure of the trapped gas mixture will equal the atmospheric pressure outside the flask. See the earlier discussion of manometers. However, there is another factor we must consider when we measure the pressure of the gas by this method. Water evaporates, and there is always gaseous water vapor above a sample of liquid water. As a gas is collected over water, it becomes saturated with water vapor, and the total pressure of the mixture equals the partial pressure of the gas plus the partial pressure of the water vapor. The pressure of the pure gas is therefore equal to the total pressure minus the pressure of the water vapor. This is referred to as the dry gas pressure, that is, the pressure of the gas only without water vapor. The vapor pressure of water, which is the pressure exerted by water vapor in equilibrium with liquid water in a closed container, depends on the temperature, figure 9.22. More detailed information on the temperature dependence of water vapor can be found in Table 9.2, and vapor pressure will be discussed in more detail in the next chapter on liquids. A graph is shown. The horizontal axis is labeled temperature, degrees C, with markings and labels provided for multiples of 20 beginning at 0 and ending at 100. The vertical axis is labeled vapor pressure, torr, with marking and labels provided for multiples of 200, beginning at 0 and ending at 800. A smooth, solid black curve extends from the origin up and to the right across the graph. The graph shows a positive trend with an increasing rate of change. On the vertical axis is 760 and an arrow pointing to it. The arrow is labeled vapor pressure at 100 degrees C. Figure 9.22. This graph shows the vapor pressure of water at sea level as a function of temperature. Vapor pressure of ice and water in various temperatures at sea level: temperature, degrees C, pressure, torr, temperature, degrees C, pressure, torr, temperature, degrees C, pressure, torr. 10-1. 95 18 15, 530 31, 8530 1916, 535 42, 2239 2017, 540 55, 3046 21 18, 750 92, 525, 322 19, 860 149, 446 123 21, 170 233, 7670 24 22, 480 355, 188, 0 25 23, 890 525, 810 92 26 25, 295 633, 9 12 10, 527 26, 799 733, 2 14 12, 0 28 28, 3 100, 0 760, 0 16 13, 6 29 30, 0 101, 0 787, 6 Table 9. 2 Example 9. 16 Pressure of a gas collected over water if 0. 200 L of argon is collected over water at a temperature of 26 degrees C and a pressure of 750 torr in a system like that shown in Figure 9. 21. What is the partial pressure of argon? Solution: according to Dalton's law, the total pressure in the bottle, 750 torr, is the sum of the partial pressure of argon and the partial pressure of gaseous water. RO rearranging this equation to solve for the pressure of argon gives letter 1d443, a R equals letter 1d443T minus letter 1d443H2O. The pressure of water vapor above a sample of liquid water at 26 degrees C is 25. 2 torr, appendix E, so letter 1d443, a R equals 750 torr minus 25. 2 torr equals 725 torr. Check your learning. A sample of oxygen collected over water at a temperature of 29 degrees C and a pressure of 764 torr has a volume of 0. 560 L. What volume would the dry oxygen from this sample have under the same conditions of temperature and pressure? Answer: 0. 537 L. Chemical stoichiometry and gases. Chemical stoichiometry describes the quantitative relationships between reactants and products in chemical reactions. We have previously measured quantities of reactants and products using masses for solids and volumes in conjunction with the molarity for solutions. Now we can also use gas volumes to indicate quantities. If we know the volume, pressure, and temperature of a gas, we can use the ideal gas equation to calculate how many moles of the gas are present. If we know how many moles of a gas are involved, we can calculate the volume of a gas at any temperature and pressure. Avogadro's law revisited: sometimes we can take advantage of a simplifying feature of the stoichiometry of gases that solids and solutions do not exhibit. All gases that show ideal behavior contain the same number of molecules in the same volume, at the same temperature and pressure. Thus, the ratios of volumes of gases involved in a chemical reaction are given by the coefficients in the equation for the reaction, provided that the gas volumes are measured at the same temperature and pressure. We can extend Avogadro's law that the volume of a gas is directly proportional to the number of moles of the gas to chemical reactions with gases. Gases combine or react in definite and simple proportions by volume, provided that all gas volumes are measured at the same temperature and pressure. For example, since nitrogen and hydrogen gases react to produce ammonia gas according to N2 letter 1d454, plus 3H2 letter 1d454, 2NH3 letter 1d454, a given volume of nitrogen gas reacts with 3 times that volume of hydrogen gas to produce 2 times that volume of ammonia gas, if pressure and temperature remain constant. The explanation for this is illustrated in Figure 9.23. According to Avogadro's law, Equal volumes of gaseous N2, H2, and NH3 at the same temperature and pressure contain the same number of molecules. Because one molecule of N2 reacts with 3 molecules of H2 to produce 2 molecules of NH3, the volume of H2 required is 3 times the volume of N2, and the volume of NH3 produced is 2 times the volume of N2. This diagram provided models of the chemical reaction written with formulas across the bottom of the figure. The reaction is written N subscript 2 plus 3H subscript 2 followed by an arrow pointing right to NH subscript 3. Just above the formulas, space-filling models are provided. Above NH subscript 2, 2 blue spheres are bonded. Above 3H subscript 2, 3 pairs of 2 slightly smaller white spheres are bonded. Above NH subscript 3, 2 molecules are shown composed each of a central blue sphere to which 3 slightly smaller white spheres are bonded. Across the top of the diagram, the reaction is illustrated with balloons. To the left is a light blue balloon, which is labeled N subscript 2. This balloon contains a single space-filling model composed of 2 bonded blue spheres. This balloon is followed by a plus sign, then 3 gray balloons which are each labeled H subscript 2. Each of these balloons similarly contain a single space-filling model composed of 2 bonded white spheres. These white spheres are slightly smaller than the blue spheres. An arrow follows that points right to 2 light green balloons, which are each labeled 2 NH subscript 3. Each light green balloon contains a space-filling model composed of a single central blue sphere to which 3 slightly smaller white spheres are bonded. Figure 9. 23 1 volume of N2 combines with 3 volumes of H2 to form 2 volumes of NH3. Example 9. 17 reaction of gases propane, C3H8G, is used in gas grills to provide the heat for cooking. What volume of O2, G, measured at 25 degrees C and 760 torr, is required to react with 2,7L of propane measured under the same conditions of temperature and pressure? Assume that the propane undergoes complete combustion. Solution: the ratio of the volumes of C3H8 and O2 will be equal to the ratio of their coefficients in the balanced equation for the reaction. C3H8, letter 1D454, plus 5O2, letter 1D454, 3CO2, letter 1D454, plus 4H2O, letter 1D459, 1 volume plus 5 volumes 3 volumes plus 4 volumes from the equation, we see that 1 volume of C3H8 will react with 5 volumes of O2. 2. 7 LC3H8 times 5 Lo 21 LC3H8 equals 13. 5 Lo 2, a volume of 13. 5 L of O2 will be required to react with 2 7 L of C3H8. Check your learning. An acetylene tank for an oxyacetylene welding torch provides 9340 L of acetylene gas, C2H2, at 0 degrees C and 1 atm. How many tanks of oxygen, each providing 7, times 103 L of O2 at 0 degrees C and 1 atm will be required to burn the acetylene? 2 C2H2 plus 5 O2 Co2 plus 2 H2O. Answer: 334 tanks, 234 times 104 L, example 9. 18 volumes of reacting gases. Ammonia is an important fertilizer and industrial chemical. Suppose that a volume of 683 billion cubic feet of gaseous ammonia, measured at 25 degrees C and 1 atm, was manufactured. What volume of H2, G, measured under the same conditions, was required to prepare this amount of ammonia by reaction with N2? N2, letter 1D454, plus 3H2, letter 1D454, 2NH3, letter 1D454. Solution: because equal volumes of H2 and NH3 contain equal numbers of molecules, and each 3 molecules of H2 that react produce 2 molecules of NH3, the ratio of the volumes of H2 and NH3 will be equal to 3. 2 volumes of NH3, in this case in units of billion ft3, will be formed from 3 volumes of H2. 683 billionth 3 NH3 times 3 billionth 3 H, 22 billionth 3 NH3 equals 1. 2 times 103 billionth 3 H2. The manufacture of 683 billion ft3 of NH3 required 1020 billion ft3 of H2. At 25 degrees C and 1 atm, this is the volume of a cube with an edge length of approximately 19 miles. Check your learning what volume of O2, G, measured at 25 degrees C and 760 torr, is required to react with 17 L of ethylene, C2H4, G, measured under the same conditions of temperature and pressure. The products are CO2 and water vapor. Answer: 510 L. Example 9. 19 volume of gaseous product. What volume of hydrogen at 27 degrees C and 723 torr may be prepared by the reaction of 88 G of gallium with an excess of hydrochloric acid, 2 Ga letter 1D460 plus 6 HCl, letter 1D44 letter 1D45E, 2 Ga Cl3, letter 1D44 letter 1D45E, plus 3 H2, letter 1D454. Solution: convert the provided mass of the limiting reactant, Ga, to moles of hydrogen produced. 88 G Ga times 1 mol Ga 69. 723 G Ga times 3 mol H, 22 mol Ga equals 0. 191 mol H2. Convert the provided temperature and pressure values to appropriate units, K and atm, respectively. And then use the molar amount of hydrogen gas and the ideal gas equation to calculate the volume of gas. Letter 1D449 equals letter 1D45B, letter 1D445, letter 1D447, letter 1D443 equals 0. 191 mol times 0. 8,206, lat mol minus 1 K minus 1 times 300 K0. 951 atm equals 4. 94 L. Check your learning. Sulfur dioxide is an intermediate in the preparation of sulfuric acid. What volume of SO2 at 343 degrees C and 121 atm is produced by burning 1 kg of sulfur in excess oxygen? Answer: 1. 30 times 103 L. How sciences interconnect greenhouse gases and climate change. The thin skin of our atmosphere keeps the Earth from being an ice planet and makes it habitable. In fact, this is due to less than 0.5% of the air molecules. Of the energy from the sun that reaches the Earth, almost 13 is reflected back into space, with the rest absorbed by the atmosphere and the surface of the Earth. Some of the energy that the Earth absorbs is re-emitted as infrared, IR, radiation, a portion of which passes back out through the atmosphere into space. Most of this IR radiation, however, is absorbed by certain atmospheric gases, effectively trapping heat within the atmosphere in a phenomenon known as the greenhouse effect. This effect maintains global temperatures within the range needed to sustain life on Earth. Without our atmosphere, the Earth's average temperature would be lower by more than 30 degrees C, nearly 60 degrees F. The major greenhouse gases, GHGs, are water vapor, carbon dioxide, methane, and ozone. Since the Industrial Revolution, human activity has been increasing the concentrations of GHGs, which have changed the energy balance and are significantly altering the Earth's climate. Figure 9.24. This diagram shows half of a two-dimensional view of the Earth in blue and green at the left of the image. A slight distance outside the hemisphere is a gray arc. A line segment connects the label atmosphere to the region between the hemisphere and the gray arc. In this region, near the surface of the Earth, the chemical formulas CO subscript 2, CH subscript 3, and N subscript 2O appear. 5 red arrows formed from wavy lines extend from green regions on the Earth out into and just beyond the region labeled atmosphere. The label infrared radiation points to one of these red arrows. At a fair distance outside of the gray arc appears a yellow circle with a jagged boundary. This circle is labeled Sun. From it extend yellow arrows with wavy lines which extend toward the Earth. 3 of the arrows extend to the green region on the Earth. One of the arrows appears to be reflected off the gray arc, causing its path to turn away from the Earth. Figure 9.24. Greenhouse gases trap enough of the sun's energy to make the planet habitable. This is known as the greenhouse effect. Human activities are increasing greenhouse gas levels, warming the planet and causing more extreme weather events. There is strong evidence from multiple sources that higher atmospheric levels of CO2 are caused by human activity. with fossil fuel burning accounting for about 34 of the recent increase in CO2. Reliable data from ice cores reveals that CO2 concentration in the atmosphere is at the highest level in the past 800,000 years. Other evidence indicates that it may be at its highest level in 20 million years. In recent years, the CO2 concentration has increased pre-industrial levels of tilde 280 ppm to more than 400 ppm today. Figure 9.25. This figure has the heading Carbon Dioxide in the Atmosphere. The first graph has a horizontal axis label, year BC, and a vertical axis label, carbon dioxide concentration, ppm. The horizontal axis labels begin at 700,000 on the left and increases by multiples of 100,000 up to 0 on the right. The vertical axis begins at 0 and increases by multiples of 50, extending up to 400. A jagged, cyclical pattern is shown that begins before 600,000 BC at under 200 ppm up to 0 BC values, appear to vary cyclically up to a high of about 300 ppm. Extending beyond 0 BC to the right, the carbon dioxide concentration appears to be on a steady increase, having reached nearly 400 ppm in recent years. The second graph is shown to magnify the portion of the graph that is most recent. This graph begins just before the year 1960 and includes markings for multiples of 10 up to the year 2010. The vertical axis begins just below 320 ppm and includes markings for all multiples of 20 up to 400 ppm. A smooth black line is shown extending through a jagged red data pattern. The trend is a steady, nearly linear increase from the lower left to the upper right on the graph. Figure 9.25 CO2 levels over the past 700,000 years were typically from 200–300 ppm, with a steep, unprecedented increase over the past 50 years. Link to learning click here to see a 2-minute video explaining greenhouse gases and global warming. Portrait of a chemist Susan Solomon, atmospheric and climate scientist Susan Solomon, Figure 9.26, is the author of one of the New York Times Books of the Year, The Coldest March, 2001, one of Time magazine's 100 Most Influential People in the World, 2008, and a working group leader of the Intergovernmental Panel on Climate Change, IPCC, which was the recipient of the 2007 Nobel Peace Prize. She helped determine and explain the cause of the formation of the ozone hole over Antarctica and has authored many important papers on climate change. She has been awarded the top scientific honors in the U.S. and France, the National Medal of Science and the Grand Medal, respectively, and is a member of the National Academy of Sciences, the Royal Society, the French Academy of Sciences, and the European Academy of Sciences. Formerly a professor at the University of Colorado, she is now at MIT and continues to work at NOAA. For more information, watch this video about Susan Solomon. A photograph is shown of Susan Solomon sitting next to a globe. Figure 9.26. Susan Solomon's research focuses on climate change and has been instrumental in determining the cause of the ozone hole over Antarctica. Credit: National Oceanic and Atmospheric Administration. Learning objectives. By the end of this section, you will be able to define and explain a fusion and diffusion, state Graham's law, and use it to compute relevant gas properties. If you have ever been in a room when a piping hot pizza was delivered, you have been made aware of the fact that gaseous molecules can quickly spread throughout a room, as evidenced by the pleasant aroma that soon reaches your nose. Although gaseous molecules travel at tremendous speeds, hundreds of meters per second, they collide with other gaseous molecules and travel in many different directions before reaching the desired target. At room temperature, a gaseous molecule will experience billions of collisions per second. The mean free path is the average distance a molecule travels between collisions. The mean free path increases with decreasing pressure. In general, the mean free path for a gaseous molecule will be hundreds of times the diameter of the molecule. In general, we know that when a sample of gas is introduced to one part of a closed container, its molecules very quickly disperse throughout the container. This process by which molecules disperse in space in response to differences in concentration is called diffusion, shown in Figure 9.27. The gaseous atoms or molecules are, of course, unaware of any concentration gradient. They simply move randomly. Regions of higher concentration have more particles than regions of lower concentrations. And so, a net movement of species from high to low concentration areas takes place. In a closed environment, diffusion will ultimately result in equal concentrations of gas throughout, as depicted in Figure 9. 27. The gaseous atoms and molecules continue to move, but since their concentrations are the same in both bulbs, the rates of transfer between the bulbs are equal. No net transfer of molecules occurs. In this figure, 3 pairs of gas-filled spheres or vessels are shown connected with a stopcock between them. In I, the figure is labeled stopcock closed. Above, the left sphere is labeled H subscript 2. It contains approximately 30 small, white, evenly distributed circles. The sphere to its right is labeled O subscript 2. It contains approximately 30 small, red, evenly distributed circles. In B, the figure is labeled stopcock open. The stopcock valve handle is now parallel to the tube connecting the two spheres. On the left, approximately 9 small, white circles and 4 small, red circles are present, with the red spheres appearing slightly closer to the stopcock. On the right side, approximately 25 small, red spheres and 21 small, white spheres are present, with the concentration of white spheres slightly greater near the stopcock. In C, the figure is labeled sometime after stopcock open. In this situation, the red and white spheres appear evenly mixed and uniformly distributed throughout both spheres. Figure 9. 27. A2 gases, H2 and O2, are initially separated. B. When the stopcock is opened, they mix together. The lighter gas, H2, passes through the opening faster than O2, so just after the stopcock is opened, more H2 molecules move to the O2 side than O2 molecules move to the H2 side. C. After a short time, both the slower-moving O2 molecules and the faster-moving H2 molecules have distributed themselves evenly on both sides of the vessel. We are often interested in the rate of diffusion, the amount of gas passing through some area per unit time. Rate of diffusion equals amount of gas passing through an area unit of time. The diffusion rate depends on several factors: temperature, the mass of the atoms or molecules, the concentration gradient, the increase or decrease in concentration from one point to another, the amount of surface area available for diffusion, and the distance the gas particles must travel. Note also that the time required for diffusion to occur is inversely proportional to the rate of diffusion, as shown in the rate of diffusion equation. A process involving movement of gaseous species similar to diffusion is a fusion, the escape of gas molecules through a tiny hole, such as a pinhole in a balloon, into a vacuum. Figure 9.28. Although diffusion and effusion rates both depend on the molar mass of the gas involved, their rates are not equal. However, the ratios of their rates are the same. This figure contains 2 cylindrical containers which are oriented horizontally. The first is labeled diffusion. In this container, approximately 25 purple and 25 green circles are shown, evenly distributed throughout the container. Trails behind some of the circles indicate motion. In the second container, which is labeled effusion, a boundary layer is evident across the center of the cylindrical container, dividing the cylinder into 2 halves. A black arrow is drawn pointing through this boundary from left to right. To the left of the boundary, approximately 16 green circles and 20 purple circles are shown again, with motion indicated by trails behind some of the circles. To the right of the boundary, only 4 purple and 16 green circles are shown. Figure 9. 28 diffusion involves the unrestricted dispersal of molecules throughout space due to their random motion. When this process is restricted to passage of molecules through very small openings in a physical barrier, the process is called effusion. If a mixture of gases is placed in a container with porous walls, the gases effuse through the small openings in the walls. The lighter gases pass through the small openings more rapidly, at a higher rate, than the heavier ones. Figure 9.29. In 1832, Thomas Graham studied the rates of effusion of different gases and formulated Graham's law of effusion. The rate of effusion of a gas is inversely proportional to the square root of its molar mass. Rate of effusion proportional to 1 letter 2133 square. This means that if two gases A and B are at the same temperature and pressure, the ratio of their effusion rates is inversely proportional to the ratio of the square roots of their molar masses. Rate of effusion of A rate of effusion of B equals letter 2133b square, letter 2133 a square. This figure shows two photos. The first photo shows an inflated orange balloon and an inflated blue balloon. Both balloons are about the same size. The second photo shows the same two balloons, but the orange one is now smaller than the blue one. Figure 9.29. The left photograph shows two balloons inflated with different gases, helium orange and argon blue. The right side photograph shows the balloons approximately 12 hours after being filled, at which time the helium balloon has become noticeably more deflated than the argon balloon, due to the greater effusion rate of the lighter helium gas. Credit, modification of work by Paul Flowers. Example 9.20. Applying Graham's law to rates of effusion. Calculate the ratio of the rate of effusion of hydrogen to the rate of effusion of oxygen. Solution. From Graham's law, we have rate of effusion of hydrogen, rate of effusion of oxygen equals 32 gmol minus 1 square 2 gmol minus 1 square equals 16 square 1 square equals 41. Hydrogen effuses 4 times as rapidly as oxygen. Check your learning. At a particular pressure and temperature, nitrogen gas effuses at the rate of 79 mls under the same conditions. At what rate will sulfur dioxide effuse? Answer: 52 mls. Example 9.21. Effusion time calculations. It takes 243 s for 446 times 10⁻5 mol z to effuse through a tiny hole. Under the same conditions, how long will it take for 46 times 10⁻5 mol ni to effuse? Solution. It is important to resist the temptation to use the times directly, and to remember how rate relates to time as well as how it relates to mass. Recall the definition of rate of effusion. Rate of effusion equals amount of gas transferred time, and combine it with Graham's law. Rate of effusion of gas Z rate of effusion of gas Ni equals letter 2133 Ni square, letter 2133 Xe square. To get amount of Z transferred time for Z amount of Ni transferred time for Ni equals letter 2133 Ni square, letter 2133 Xe square. Noting that amount of A equals amount of B, and solving for time for Ni. Amount of Z time for Z amount of net time for Ni equals time for net time for Z equals letter 2133 Ni square, letter 2133 Xe square equals letter 2133 Ni square, letter 2133 Xe square. And substitute values. Time for Ni 243s equals 20, 2 gmol 131, 3 gmol equals 0, 392. Finally, solve for the desired quantity. Time for Ni equals 0, 392 times 243s equals 95. 3s. Note that this answer is reasonable. Since Ni is lighter than Z, the effusion rate for Ni will be larger than that for Z, which means the time of effusion for Ni will be smaller than that for Z. Check your learning. A party balloon filled with helium deflates to 23 of its original volume in 80 hours. How long will it take an identical balloon filled with the same number of moles of air, m, equals 28, 2g/mol, to deflate to 12 of its original volume? Answer: 32h. Example 9.22. Determining molar mass using Graham's law. An unknown gas effuses 1.66 times more rapidly than Co2. What is the molar mass of the unknown gas? Can you make a reasonable guess as to its identity? Solution. From Graham's law, we have rate of effusion of unknown rate of effusion of Co2 equals letter 2133 CO, 2 square letter 2133, letter 1d448, letter 1d45b, letter 1d458, letter 1d45b, letter 1d45c, letter 1d464 square. Plug in known data. 1. 661 equals 44. 0 g/mol square letter 2133, letter 1d448, letter 1d45b, letter 1d458, letter 1d45b, letter 1d45c, letter 1d464 square. Solve. Letter 2133, letter 1d448, letter 1d45b, letter 1d458, letter 1d45b, letter 1d45c, letter 1d464 equals 44. 0 g/mol. 1. 66 of 2 equals 16. 0 g/mol. The gas could well be CH4, the only gas with this molar mass. Check your learning. Hydrogen gas effuses through a porous container 8. 97 times faster than an unknown gas. Estimate the molar mass of the unknown gas. Answer: 162 g/mol. How sciences interconnect. Use of diffusion for nuclear energy applications. Uranium enrichment. Gaseous diffusion has been used to produce enriched uranium for use in nuclear power plants and weapons. Naturally occurring uranium contains only 0.72% of 235U, the kind of uranium that is fissile, that is, capable of sustaining a nuclear fission chain reaction. Nuclear reactors require fuel that is 25% 235U, and nuclear bombs need even higher concentrations. One way to enrich uranium to the desired levels is to take advantage of Graham's law. In a gaseous diffusion enrichment plant, uranium hexafluoride, UF6, the only uranium compound that is volatile enough to work, is slowly pumped through large cylindrical vessels called diffusers, which contain porous barriers with microscopic openings. The process is one of diffusion because the other side of the barrier is not evacuated. The 235 UF6 molecules have a higher average speed and diffuse through the barrier a little faster than the heavier 238 UF6 molecules. The gas that has passed through the barrier is slightly enriched in 235 UF6, and the residual gas is slightly depleted. The small difference in molecular weights between 235 UF6 and 238 UF6, only about 0.4% enrichment, is achieved in one diffuser, figure 930. But by connecting many diffusers in a sequence of stages, called a cascade, the desired level of enrichment can be attained. This figure shows a large cylindrical container oriented horizontally. A narrow tube or pipe, which is labeled porous barrier, runs horizontally through the center of the tube and extends a short distance out from the left and right ends of the cylinder. At the far left, an arrow points right into the tube. This arrow is labeled uranium hexafluoride UF subscript 6. A line segment connects the label high-pressure feed tube to the tube where it enters the cylinder. In the short region of tube outside the cylinder, 5 small purple circles and 4 small green circles are present. Inside the cylinder, an arrow points right through the tube, which contains many evenly distributed purple circles and a handful of green circles which decrease in quantity moving left to right through the cylinder. Curved arrows extend from the inner area of the tube into the outer region of the cylinder. 3 of these arrows point into the area above the tube, and 3 point into the area below. 2 line segments extend from the label higher speed superscript 235 UF subscript 6 diffuses through barrier faster than superscript 238 UF subscript 6 to 2 green circles in the space above the tube. In the short section of tubing just outside the cylinder, 8 small purple circles are present. An arrow labeled depleted superscript 238 UF subscript 6 points right, extending from the end of this tube. The larger space outside the tube contains approximately 100 evenly distributed small green circles and only 5 purple circles. 8 of the purple circles appear at the left end of the cylinder. A tube exits the lower right end of the cylinder. It has 5 green circles followed by a right-pointing arrow and the label enriched superscript 235 UF subscript 6. Figure 9:30 in a diffuser, gaseous UF6 is pumped through a porous barrier, which partially separates 235 UF6 from UF. The UF6 must pass through many large diffuser units to achieve sufficient enrichment in 235U. The large-scale separation of gaseous 235 UF6 from 238 UF6 was first done during the World War II at the Atomic Energy Installation in Oak Ridge, Tennessee, as part of the Manhattan Project, the development of the first atomic bomb. Although the theory is simple, this required surmounting many daunting technical challenges to make it work in practice. The barrier must have tiny, uniform holes about 10.6 cm in diameter and be porous enough to produce high flow rates. All materials, the barrier, tubing, surface coatings, lubricants, and gaskets, need to be able to contain, but not react with, the highly reactive and corrosive UF6. Because gaseous diffusion plants require very large amounts of energy, to compress the gas to the high pressures required and drive it through the diffuser cascade, to remove the heat produced during compression, and so on. It is now being replaced by gas centrifuge technology, which requires far less energy. A current hot political issue is how to deny this technology to Iran, to prevent it from producing enough enriched uranium for them to use to make nuclear weapons. Learning objectives: state the postulates of the kinetic molecular theory. Use this theory's postulates to explain the gas laws. The gas laws that we have seen to this point, as well as the ideal gas equation, are empirical, that is, they have been derived from experimental observations. The mathematical forms of these laws closely describe the macroscopic behavior of most gases at pressures less than about 1 or 2 atm. Although the gas laws describe relationships that have been verified by many experiments, they do not tell us why gases follow these relationships. The kinetic molecular theory, KMT, is a simple microscopic model that effectively explains the gas laws described in previous modules of this chapter. This theory is based on the following 5 postulates described here. Note: the term molecule will be used to refer to the individual chemical species that compose the gas, although some gases are composed of atomic species, for example, the noble gases. Gases are composed of molecules that are in continuous motion, traveling in straight lines and changing direction only when they collide with other molecules or with the walls of a container. The molecules composing the gas are negligibly small compared to the distances between them. The pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. Gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic, do not involve a loss of energy. The average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. The test of the KMT and its postulates is its ability to explain and describe the behavior of a gas. The various gas laws can be derived from the assumptions of the KMT, which have led chemists to believe that the assumptions of the theory accurately represent the properties of gas molecules. We will first look at the individual gas laws: Boyle's, Charles's, Amundsen's, Avogadro's, and Dalton's laws, conceptually to see how the KMT explains them. Then, we will more carefully consider the relationships between molecular masses, speeds, and kinetic energies with temperature, and explain Graham's law. The kinetic molecular theory explains the behavior of gases, part I, recalling that gas pressure is exerted by rapidly moving gas molecules and depends directly on the number of molecules hitting a unit area of the wall per unit of time. We see that the KMT conceptually explains the behavior of a gas as follows. Amundsen's law: if the temperature is increased, the average speed and kinetic energy of the gas molecules increase. If the volume is held constant, the increased speed of the gas molecules results in more frequent and more forceful collisions with the walls of the container, therefore increasing the pressure, figure 9.31. Charles's law: if the temperature of a gas is increased, a constant pressure may be maintained only if the volume occupied by the gas increases. This will result in greater average distances traveled by the molecules to reach the container walls, as well as increased wall surface area. These conditions will decrease both the frequency of molecule wall collisions and the number of collisions per unit area, the combined effects of which balance the effect of increased collision forces due to the greater kinetic energy at the higher temperature. Boyle's law: if the gas volume of a given amount of gas at a given temperature is decreased, that is, if the gas is compressed, the molecules will be exposed to a decreased container wall area. Collisions with the container wall will therefore occur more frequently, and the pressure exerted by the gas will increase, figure 9.31. Avogadro's law: at constant pressure and temperature, the frequency and force of molecule wall collisions are constant. Under such conditions, increasing the number of gaseous molecules will require a proportional increase in the container volume in order to yield a decrease in the number of collisions per unit area to compensate for the increased frequency of collisions, figure 9.31. Dalton's law: because of the large distances between them, the molecules of one gas in a mixture bombard the container walls with the same frequency whether other gases are present or not, and the total pressure of a gas mixture equals the sum of the partial pressures of the individual gases. This figure shows 3 pairs of pistons and cylinders. In I, which is labeled Charles's law, the piston is positioned for the first cylinder so that just over half of the available volume contains 6 purple spheres with trails behind them. The trails indicate movement. Orange dashes extend from the interior surface of the cylinder where the spheres have collided. This cylinder is labeled baseline. In the second cylinder, the piston is in the same position, and the label heat is indicated in red capitalized text. 4 red arrows with wavy stems are pointing upward to the base of the cylinder. The 6 purple spheres have longer trails behind them, and the number of orange dashes indicating points of collision with the container walls has increased. A rectangle beneath the diagram states, temperature increased, volume constant equals increased pressure. In B, which is labeled Boyle's law, the first baseline cylinder shown is identical to the first cylinder in A. In the second cylinder, the piston has been moved, decreasing the volume available to the 6 purple spheres to half of the initial volume. The orange dashes indicating points of collision with the container walls has increased. This second cylinder is labeled volume decreased. A rectangle beneath the diagram states, volume decreased, wall area decreased equals increased pressure. In C, which is labeled Avogadro's law, the first baseline cylinder shown is identical to the first cylinder in A and the second cylinder. The number of purple spheres has changed from 6 to 12, and volume has doubled. This second cylinder is labeled increased gas. A rectangle beneath the diagram states, at constant pressure, more gas molecules added equals increased volume. Figure 9.31a, when gas temperature increases, gas pressure increases due to increased force and frequency of molecular collisions. B, when volume decreases, gas pressure increases due to increased frequency of molecular collisions. C, when the amount of gas increases at a constant pressure, volume increases to yield a constant number of collisions per unit wall area per unit time. Molecular speeds and kinetic energy. The previous discussion showed that the KMT qualitatively explains the behaviors described by the various gas laws. The postulates of this theory may be applied in a more quantitative fashion to derive these individual laws. To do this, we must first look at speeds and kinetic energies of gas molecules and the temperature of a gas sample. In a gas sample, individual molecules have widely varying speeds. However, because of the vast number of molecules and collisions involved, the molecular speed distribution and average speed are constant. This molecular speed distribution is known as a Maxwell-Boltzmann distribution, and it depicts the relative numbers of molecules in a bulk sample of gas that possesses a given speed, figure 9.32. A graph is shown. The horizontal axis is labeled speed u, m divided by s. This axis is marked by increments of 20 beginning at 0 and extending up to 120. The vertical axis is labeled fraction of molecules. A positively or right-skewed curve is shown in red, which begins at the origin and approaches the horizontal axis around 120 m per s. At the peak of the curve, a point is indicated with a black dot and is labeled V subscript p. A vertical dashed line extends from this point to the horizontal axis, at which point the intersection is labeled V subscript p. Slightly to the right of the peak, a second black dot is placed on the curve. This point is labeled V subscript RMS. A vertical dashed line extends from this point to the horizontal axis, at which point the intersection is labeled V subscript RMS. The label O subscript 2 at t equals 300 K appears in the open space to the right of the curve. Figure 9.32, the molecular speed distribution for oxygen gas at 300 K is shown here. Very few molecules move at either very low or very high speeds. The number of molecules with intermediate speeds increases rapidly up to a maximum, which is the most probable speed, then drops off rapidly. Note that the most probable speed nup is a little less than 400 ms, while the root mean square speed erms is closer to 500 ms. The kinetic energy, Ke, of a particle of mass m, and speed, u, is given by Ke equals 12 letter 1d45a letter 1d4622. Expressing mass in kilograms and speed in meters per second will yield energy values in units of joules. J equals kg m2 s2. To deal with a large number of gas molecules, we use averages for both speed and kinetic energy. In the kmt, the root mean square speed of a particle, erms, is defined as the square root of the average of the squares of the speeds, with n equals the number of particles. Letter 1d462 rms equals letter 1d462. 2 square equals letter 1d462 21, plus letter 1d462 22, plus letter 1d462 23, plus letter 1d462 24, plus letter 1d45b square. The average kinetic energy for a mole of particles, K eV, is then equal to K eV equals 12, letter 1d440, letter 1d462 to RMS, where m is the molar mass, expressed in units of kg/mol. The K eV of a mole of gas molecules is also directly proportional to the temperature of the gas, and may be described by the equation. K eV equals 32 letter 1d445 letter 1d447, where R is the gas constant, and T is the Kelvin temperature. When used in this equation, the appropriate form of the gas constant is 8. 314 J/mol K, 8 314 kg m to s 2 mol 1 K1. These two separate equations for K eV may be combined and rearranged to yield a relation between molecular speed and temperature. 12 mu to RMS equals 32 letter 1d445 letter 1d447. Letter 1d462 RMS equals 3 letter 1d445 letter 1d447 letter 1d440 square. Example 9. 23. Calculation of erms. Calculate the root mean square speed for a nitrogen molecule at 30 degrees C. Solution. Convert the temperature into Kelvin. 30 degrees C plus 273 equals 303 K. Determine the molar mass of nitrogen in kilograms. 28. 0 g 1 mol times 1 kg 1000 g equals 0. 0, 28 kg/mol. Replace the variables and constants in the root mean square speed equation, replacing joules with the equivalent kg m to s2. Letter 1d462 rms equals 3 letter 1d445 letter 1d447 letter 1d440 square. Letter 1d462 rms equals 3, 8, 314 j/mol k, 303 k, 0. 0, 28 kg/mol square equals 2. 70 times 105 m to s minus 2 square equals 519 m/s. Check your learning. Calculate the root mean square speed for a mole of oxygen molecules at 23 degrees C. Answer, 441 ms. If the temperature of a gas increases, its K eV increases, more molecules have higher speeds and fewer molecules have lower speeds, and the distribution shifts toward higher speeds overall. That is, to the right. If temperature decreases, K eV decreases, more molecules have lower speeds and fewer molecules have higher speeds, and the distribution shifts toward lower speeds overall. That is, to the left. This behavior is illustrated for nitrogen gas in Figure 9. 33. A graph with 4 positively or right-skewed curves of varying heights is shown. The horizontal axis is labeled speed u, m divided by s. This axis is marked by increments of 500 beginning at 0 and extending up to 1500. The vertical axis is labeled fraction of molecules. The label n subscript 2 appears in the open space in the upper right area of the graph. The tallest and narrowest of these curves is labeled 100K. Its right end appears to touch the horizontal axis around 700 m per s. It is followed by a slightly wider curve which is labeled 200K. That is about 3/4 of the height of the initial curve. Its right end appears to touch the horizontal axis around 850 m per s. The third curve is significantly wider and only about half the height of the initial curve. It is labeled 500K. Its right end appears to touch the horizontal axis around 1450 m per s. The final curve is only about 1/3 the height of the initial curve. It is much wider than the others, so much so that its right end has not yet reached the horizontal axis. This curve is labeled 1000K. Figure 9. 33. The molecular speed distribution for nitrogen gas. N2 shifts to the right and flattens as the temperature increases. It shifts to the left and heightens as the temperature decreases. At a given temperature, all gases have the same k-eV for their molecules. Gases composed of lighter molecules have more high-speed particles and a higher ERMS, with a speed distribution that peaks at relatively higher speeds. Gases consisting of heavier molecules have more low-speed particles, a lower ERMS, and a speed distribution that peaks at relatively lower speeds. This trend is demonstrated by the data for a series of noble gases shown in Figure 9.34. A graph is shown with 4 positively or right-skewed curves of varying heights. The horizontal axis is labeled speed u, m divided by s. This axis is marked by increments of 500 beginning at 0 and extending up to 3000. The vertical axis is labeled fraction of molecules. The tallest and narrowest of these curves is labeled xe. Its right end appears to touch the horizontal axis around 600 m per s. It is followed by a slightly wider curve which is labeled ar. That is about half the height of the initial curve. Its right end appears to touch the horizontal axis around 900 m per s. The third curve is significantly wider and just over a third of the height of the initial curve. It is labeled ne. Its right end appears to touch the horizontal axis around 1200 m per s. The final curve is only about 1/4 the height of the initial curve. It is much wider than the others, so much so that its right reaches the horizontal axis around 2500 m per s. This curve is labeled he. Figure 9.34. Molecular speed is directly related to molecular mass. At a given temperature, lighter molecules move faster on average than heavier molecules. Link to learning. The gas simulator may be used to examine the effect of temperature on molecular speeds. Examine the simulator's energy histograms, molecular speed distributions, and species information, which gives average speed values for molecules of different masses at various temperatures. The kinetic molecular theory explains the behavior of gases, Part II. According to Graham's law, the molecules of a gas are in rapid motion, and the molecules themselves are small. The average distance between the molecules of a gas is large compared to the size of the molecules. As a consequence, gas molecules can move past each other easily and diffuse at relatively fast rates. The rate of effusion of a gas depends directly on the average speed of its molecules. Effusion rate proportional to letter 1d462 RMS. Using this relation, and the equation relating molecular speed to mass, Graham's law may be easily derived as shown here. Letter 1d462 RMS equals 3, letter 1d445, letter 1d447, letter 1d440 square. Letter 1d440 equals 3, letter 1d445, letter 1d447, letter 1d462 RMS equals 3, letter 1d445, letter 1d447, letter 1d462 2. Effusion rate B-Bay. The ratio of the rates of effusion is thus derived to be inversely proportional to the ratio of the square roots of their masses. This is the same relation observed experimentally and expressed as Graham's law. Learning objectives. By the end of this section, you will be able to describe the physical factors that lead to deviations from ideal gas behavior. Explain how these factors are represented in the van der Waals equation. Define compressibility, Z, and describe how its variation with pressure reflects non-ideal behavior. Quantify non-ideal behavior by comparing computations of gas properties using the ideal gas law and the van der Waals equation. Thus far, the ideal gas law, PV equals nRT, has been applied to a variety of different types of problems, ranging from reaction stoichiometry and empirical and molecular formula problems to determining the density and molar mass of a gas. As mentioned in the previous modules of this chapter, however, the behavior of a gas is often non-ideal, meaning that the observed relationships between its pressure, volume, and temperature are not accurately described by the gas laws. In this section, the reasons for these deviations from ideal gas behavior are considered. One way in which the accuracy of PV equals nRT can be judged is by comparing the actual volume of 1 mole of gas, its molar volume, Vm, to the molar volume of an ideal gas at the same temperature and pressure. This ratio is called the compressibility factor, Z, with Z equals molar volume of gas at same letter 1d447 A ND letter 1d443 molar volume of ideal gas at same letter 1d447, a ND letter 1d443 equals letter 1d443, letter 1d449, letter 1d45a, letter 1d445, letter 1d447. Measured. Ideal gas behavior is therefore indicated when this ratio is equal to 1, and any deviation from 1 is an indication of non-ideal behavior. Figure 9:35 shows plots of Z over a large pressure range for several common gases. A graph is shown. The horizontal axis is labeled P atm. Its scale begins at 0 with markings provided by multiples of 200 up to 1000. The vertical axis is labeled Zila Kp. This scale begins at 0 and includes multiples of 0, 5 up to 20. 6 curves are drawn of varying colors. One of these curves is a horizontal, light purple line extending right from 1 kp on the vertical axis, which is labeled ideal gas. The region of the graph beneath this line is shaded tan. The remaining curves also start at the same point on the vertical axis. An orange line extends to the upper right corner of the graph, reaching a value of approximately 1.7 kp at 1000 atm. This orange curve is labeled H subscript 2. A blue curve dips below the horizontal ideal gas line initially, then increases to cross the line just past 200 atm. This curve reaches a value of nearly 2 kp at about 800 atm. This curve is labeled N subscript 2. A red curve dips below the horizontal ideal gas line initially, then increases to cross the line just past 400 atm. This curve reaches a value of nearly 15 kp at about 750 atm. This curve is labeled O subscript 2. A purple curve dips below the horizontal ideal gas line, dipping even lower than the O subscript 2 curve initially, then increases to cross the ideal gas line at about 400 atm. This curve reaches a value of nearly 2 kp at about 850 atm. This curve is labeled CH subscript 4. A yellow curve dips below the horizontal ideal gas line, dipping lower than the other curves to a minimum of about 0.4 kp at about 0.75 atm, then increases to cross the ideal gas line at about 500 atm. This curve reaches a value of about 16 kp at about 900 atm. This curve is labeled CO subscript 2. Figure 9:35. A graph of the compressibility factor, Z versus pressure, shows that gases can exhibit significant deviations from the behavior predicted by the ideal gas law. As is apparent from Figure 9:35, the ideal gas law does not describe gas behavior well at relatively high pressures. To determine why this is, consider the differences between real gas properties and what is expected of a hypothetical ideal gas. Particles of a hypothetical ideal gas have no significant volume and do not attract or repel each other. In general, real gases approximate this behavior at relatively low pressures and high temperatures. However, at high pressures, the molecules of a gas are crowded closer together, and the amount of empty space between the molecules is reduced. At these higher pressures, the volume of the gas molecules themselves becomes appreciable relative to the total volume occupied by the gas. The gas therefore becomes less compressible at these high pressures, and although its volume continues to decrease with increasing pressure, this decrease is not proportional as predicted by Boyle's law. At relatively low pressures, gas molecules have practically no attraction for one another because they are, on average, so far apart, and they behave almost like particles of an ideal gas. At higher pressures, however, the force of attraction is also no longer insignificant. This force pulls the molecules a little closer together, slightly decreasing the pressure if the volume is constant or decreasing the volume at constant pressure. Figure 9:36. This change is more pronounced at low temperatures because the molecules have lower Ke relative to the attractive forces, and so they are less effective in overcoming these attractions after colliding with one another. This figure includes two diagrams. Each involves two lavender-shaded boxes that contain 14 relatively evenly distributed purple spheres. The first box and on the left is labeled ideal. In the second, slightly smaller box on the right, A nearly centrally located purple sphere has 6 double-headed arrows extending outward from it to nearby spheres. This box is labeled real. In B, in the first box on the left, a single arrow points to a purple sphere at the right side that appears to be moving and impacting the right side of the box. There are no other spheres positioned near the right edge. This box is labeled ideal. The second box on the right shows the same image but has 5 double-headed arrows radiating out to the top, bottom, and left to other spheres. This box is labeled real. Figure 9.36. A. Attractions between gas molecules serve to decrease the gas volume at constant pressure, compared to an ideal gas whose molecules experience no attractive forces. B. These attractive forces will decrease the force of collisions between the molecules and container walls, therefore reducing the pressure exerted at constant volume compared to an ideal gas. There are several different equations that better approximate gas behavior than does the ideal gas law. The first, and simplest, of these was developed by the Dutch scientist Johannes van der Waals in 1879. The van der Waals equation improves upon the ideal gas law by adding 2 terms, one to account for the volume of the gas molecules and another for the attractive forces between them. This figure shows the equation PV equals nRT, with the P in blue text and the V in red text. This equation is followed by a right-pointing arrow. Following this arrow, to the right in blue text appears the equation P minus a n superscript 2 divided by V squared, which is followed by the red text, V minus NB. This is followed in black text with equals nRT. Beneath the second equation appears the label correction for molecular attraction, which is connected with a line segment to V squared. A second label, correction for volume of molecules, is similarly connected to NB, which appears in red. The constant A corresponds to the strength of the attraction between molecules of a particular gas, and the constant B corresponds to the size of the molecules of a particular gas. The correction to the pressure term in the ideal gas law is N to AV2, and the correction to the volume is NB. Note that when V is relatively large and N is relatively small, both of these correction terms become negligible, and the van der Waals equation reduces to the ideal gas law, PV equals nRT. Such a condition corresponds to a gas in which a relatively low number of molecules is occupying a relatively large volume. That is, a gas at a relatively low pressure. Experimental values for the van der Waals constants of some common gases are given in Table 9, 3 values of van der Waals constants for some common gases. Gas A L2 atm/mol2, B L/mol. N21, 390, 391. O21, 360, 318. Co23, 590, 427. H2O5, 460, 305. He0, 03420, 237. CCl 420, 40, 1383. Table 9.3. At low pressures, the correction for intermolecular attraction, A, is more important than the one for molecular volume, B. At high pressures and small volumes, the correction for the volume of the molecules becomes important because the molecules themselves are incompressible and constitute an appreciable fraction of the total volume. At some intermediate pressure, the two corrections have opposing influences, and the gas appears to follow the relationship given by PV equals nRT over a small range of pressures. This behavior is reflected by the dips in several of the compressibility curves shown in Figure 9.35. The attractive force between molecules initially makes the gas more compressible than an ideal gas. As pressure is raised, Z decreases with increasing P. At very high pressures, the gas becomes less compressible, Z increases with P, as the gas molecules begin to occupy an increasingly significant fraction of the total gas volume. Strictly speaking, the ideal gas equation functions well when intermolecular attractions between gas molecules are negligible, and the gas molecules themselves do not occupy an appreciable part of the whole volume. These criteria are satisfied under conditions of low pressure and high temperature. Under such conditions, the gas is said to behave ideally, and deviations from the gas laws are small enough that they may be disregarded. This is, however, very often not the case. Example 9.24. Comparison of ideal gas law and van der Waals equation. A 425L flask contains 346 mol CO2 at 229 degrees C. Calculate the pressure of this sample of CO2. A. From the ideal gas law. B. From the van der Waals equation. C. Explain the reason. S. For the difference. Solution. A. From the ideal gas law. Letter 1 D443 equals letter 1 D45B, letter 1 D445, letter 1 D447, letter 1 D449 equals 3. 46 mol times 0. 0.8206 lat mol minus 1 K minus 1 times 502 K4. 25 L equals 33. 5 atm. B. From the van der Waals equation. P plus N to letter 1 D440, letter 1 D4492 times letter 1 D449 minus letter 1 D45B, letter 1 D44F equals letter 1 D45B, letter 1 D445, letter 1 D447, letter 1 D443 equals letter 1 D45B, letter 1 D445, letter 1 D447, letter 1 D449 minus letter 1 D45B, letter 1 D44F minus letter 1 D45B to AV2. Letter 1 D443 equals 3. 46 mol times 0. 0.8206 lat mol minus 1 K minus 1 times 502 K4. 25 L minus 3. 46 mol times 0. 0.427 L mol minus 1 minus 3. 46 mol 2 times 3. 59 L to atmol 2 4. 25 L2. This finally yields P equals 32. 4 atm. C. This is not very different from the value from the ideal gas law because the pressure is not very high and the temperature is not very low. The value is somewhat different because CO2 molecules do have some volume and attractions between molecules, and the ideal gas law assumes they do not have volume or attractions. Check your learning. A 560 ml flask contains 21, 3G N2 at 145 degrees C. Calculate the pressure of N2. A. From the ideal gas law. B. From the van der Waals equation. C. Explain the reason. S. For the difference. Answer. A. 46, 562 atm. B. 46, 594 atm. C. The van der Waals equation takes into account the volume of the gas molecules themselves, as well as intermolecular attractions.